Okay, good morning, everyone. I think we're going to get started a couple of minutes later than planned. And without saying it, I'm going to do a little bit of housekeeping afterwards. But first, it gives me great pleasure to welcome Professor Nick Plant, our Deputy Vice-Chancellor for Research and Innovation, to open the exchange for the second day. Nick.
Good morning, everybody. Why does everybody always sit at the back? We're not that scary. Welcome. This is the 5th year for Bragg, and I think particularly given that Bragg really grew through COVID, this is an important celebration because it marks a point of change, and I'll talk about why I think it does as I go through my introductory remarks. But one thing I was really clear of, I have been and launched one of the days at every single Bragg Exchange since we came back out of COVID. And many of you have been in the audience through those. And I was determined I wasn't going to give the same old speech I give every single year. I was going to try and do something different. And I was reflecting on what does Bragg actually mean to the university, to the wider community, and where should we be thinking about for the next 5 years? And I'm going to start with what you might think is a slightly odd point, which is the Staff Education Conference that we had in this very room 2 weeks ago or so. And I was on a panel talking about pedagogical research. And the question was, what is pedagogical research? Is it any good, and should we be doing it? So why does that have anything to do with Bragg? Well, because my opening remark was, how do you define research? If you're a materials researcher, what you do is you develop new materials, you think and characterize them and test them, and then you apply them into the real world to make an impact. And then I went on to talk about how that's the same for pedagogical research. The question you should be asking yourself is, why did I pick materials research rather than climate science or molecular biology, where I come from is my history? And the answer is because it was the first thing that came into my mind when I thought about a success at the University of Leeds. And that is an absolute testament to every single person sitting in this room, all of the members of Bragg outside of that room, the wider community across Royce that have really helped the materials agenda take centre face, not just with universities, but with government as well. So I genuinely think in the last 5 years, you've made a huge difference. You've built a genuine community that makes a big difference. If you look through what's happened just in the last year, the new training courses, there's absolutely no point in being at the forefront of an area if you are not training people to use those new technologies, if you're not bringing in the next generation of researchers and scientists and policymakers who will understand the potential and apply it. Innovative outreach. I always think that Bragg has led the way in terms of how our interdisciplinary research centres drive outreach and work with communities. And again, you've done that superbly this year. But also, and probably most critically, just world-leading fundamental research. We do not address the challenges of today without having done fundamental research 5 years, 10 years, even 15 years ago. You think back to the development of the COVID vaccine. That was based upon mRNA technology that was 15 years old, but it was fundamental research that drove the ability to produce the vaccine. The fundamental research that we do in Bragg and in materials is what will drive the solutions to global challenges in the next 10, 15 years. So we have to be proud of the huge number of fantastic publications in fundamental research. So what do we do in the next 5 years? What's going to happen when I am standing here or possibly listening to the live stream, sitting on a beach somewhere, drinking gin and tonic? We really need to align to the government missions. You've seen the announcements in this week about AI, the talk about the green agenda, security, healthcare transformation, growth and productivity. Materials research and this community is going to play an incredibly important part for the university in helping to address all of the government missions, but also for the government and the UK in driving this forward. You need to think about how what you do fits in with that, and quite frankly, how you can exploit the opportunities. I do expect this area, I'm looking at, where's Giles gone? He's hidden. Giles isn't there, you're right at the back. Giles and Edmund, who were part of the superb REF team last time, I do expect materials research to be one of our star areas in REF 2029, not just in outputs, not just in impact, but actually in the PCE, the culture of gender as well. Because one of the things that the Bragg community has shown is how you build a positive research culture. I think we do have challenges in society at the moment. We have technological challenges, both to address new problems and technological debt across a huge proportion of society. We have financial challenges across, well, everywhere, let's be honest. And we also have ethical challenges. The more we push boundaries, the more we have to think about whether these are doors we want to open, and if we do, how we do it in a safe and ethical way. I think that Bragg can be part of that conversation and drive it forward. So it's a tough ask, but I'm in my job because I'm supposed to ask the tough questions. I am pretty confident that if I stand here in 5 years' time, the Bragg Centre for Materials Research will have met most of these challenges and probably, as it keeps doing, exceeding my expectations. So I am really pleased to be able to open this. I'm going to, before I finish, just start, I suspect, the congratulations and thank yous to Andy, because while I have mentioned a number of people who drive Bragg, the Bragg community would not be what it is without Andy as a driving force. So I'm going to make him embarrassed. Give him a round of applause, people. Have a fantastic day. I'm now going to pass back to the blushing man.
Okay, thank you very much, Nick. And thank you very much for the round of applause. So just before we get started, for some of the people that have arrived today rather than yesterday, I'll just give a very quick refresh on some of the quick housekeeping. Importantly, fire alarms. We're not expecting any fire alarms. The test was this morning at 8 o'clock. And so if you hear the fire alarm, then we do need to exit the building. There are fire escapes either side at the front here and obviously out through the back, about the back of the lecture theatre. And the congregation point is out that side of the building on the grass. In terms of poster voting, today is the final day to vote for your posters. We've got one final session at lunchtime. And hopefully you're all aware now that in the back of your name badge, there is a poster voting slip. Please mark a poster, a number on it, and drop it in one of the boxes by the end of the lunchtime session today, so we can award some poster prizes. There are 3 up for grabs, 2 runners-up, and 1 best poster in session. And with that, I think that's about the only comments I have to make before we get started. So I'm going to hand over to Professor Chris Marrows to lead our next session. Thank you.
Thanks, Andy. Hi, so good morning, everyone. I'm Chris Marrows. I'm from the School of Physics and Astronomy here in Leeds, and I'm the theme lead in Bragg for the theme of electronic and photonic materials, and so that means that I'm the chair for that session this morning. So our first speaker is Professor Richard Curry from the University of Manchester. We're delighted to welcome him. He's Professor of Advanced Electronic Materials there. Previously, he's been at Queen Mary's, Southampton, Surrey. He joined Manchester in 2016, focusing on new photonic materials and devices, and specifically in doped solid-state materials for quantum metrologies. He co-leads EPSRC's Materials for Quantum Network. He has a very broad research portfolio. I know it best. I'm not a member of the NAME program grant myself, but colleagues in condensed matter physics are, and I know that's a very vibrant and active program of research. So his talk today covers work on nanoscale advanced materials engineering, and as a special point, it's his birthday treat today to come and give this talk. So we'll welcome him and wish him a happy birthday at the same time. Please, Richard.
Okay, yes?
There we go.
Right, okay, and Edmund promised me I could speak for 1 minute for every year that I've been alive. So, so you can time this, and then you'll get... Okay, so work entitled Nanoscale Advanced Materials Engineering. An alternative was how to build a quantum computer in 3 easy steps, but they're not so easy. But anyway, so I'm going to do acknowledgements first, and quite fittingly, here's a picture of the program grant team from our early days outside the Bragg Centre. So I thought I would show that. And a lot of this work has been done really by Maddie, who's here, Mason, who is here, and Janet, who's hiding at the back always, helped by many other people in this group. So, I'm going to talk about quantum computing, or how we get there, and quantum computing requires qubits. Qubits are the equivalent of bits in a normal computer, with the advantage that you can be in the 2 states at the same time, and therefore you get 2 to the n scaling. So you can essentially address problems which you just couldn't ever do using a classical computer. How to build a quantum computer? Well, you've got to choose what your qubit flavor is going to be, and there's many options out there. So at the bottom here, topological insulators. These are probably the furthest away from being realized, but have huge potential advantages. And actually, we are doing some work on these materials with colleagues at Leeds. So you make these materials here, and we're looking at how we can modify and control them. NV centers in diamond. So this is single photon emitter sources. We work on those as well. That's for using photons as a medium. I'm not going to talk about that today. We also do some work on superconducting systems using what are called squid loops, so currents which create magnetic moments which you can use as your qubit. But I'm not going to talk about that either. What I am going to talk about is what you see up on the left here, which is essentially dopants in solid-state materials, and in silicon in particular, but this also applies to germanium and other systems potentially going forwards. So the question is, how do you build a qubit in a solid-state material? Well, you need to put an object in there which has these quantum states which you can use. And typically, we use electrons as one way of doing that because they have spin up, spin down. So if I put into silicon a donor which has an extra electron around it, we can use that as the basis of the qubit. And so I'm going to talk to you about the technology, about how we're going to go about doing that, and what some of the challenges are we need to address on the way. So, Lucy, someone's edited my slides. So the problem is, you see, what you've done, I was trying to look back for a moment in life where I had hair, but it seems I never had hair. So this goes back to beginning of the quantum program in the UK, where a number of us got together at Cambridge and were thinking about, well, how the heck can we build a quantum computer? So myself, Meta was there. He had longer hair in those days. He's still got long hair. Jason was there, Jason Smith from Oxford. He still has hair. I don't know what happened. It's unfair. Anyway, and we decided that ion implantation is probably quite a good way to do it, especially in silicon, because if we can get it right, we can use all of the scaling which we use for standard CMOS electronics, and use that to build a quantum computer, which needs to be of the order of at least 10,000, if not 1 million qubits, to actually get to beyond, well, totally error-corrected quantum computing, right? And that's a big challenge, having 1 million of these things and connecting them all up. So we looked at the landscape of what techniques you could use to do this. And as I go through this talk, this is, lots of materials work in here. Just try and keep a note of a number of different techniques that we use in our research. It's actually quite amazing, what we have to do to understand the materials and then use them. But there was no system at the time which gave the resolution, spatial resolution, and also determinacy. What this means is if I put one thing there, one atom, I know it's one atom and it isn't two, or it's not zero. Right? So there was no technology which could do that at scale. So this space in this top right here was what we're aiming for. And so really the first bit of a talk is just showing that we've done this, we've made a technology to do this, and then the second bit is really, well, the main bit is about how we've applied that to this problem. Okay, so what did we make? Well, we ended up working with a UK company, Ion Optica, and we made what we're calling the PNAME tool, Platform for Nanoscale Advanced Materials Engineering. And what this effectively is a focused ion beam tool, which has an integrated electron beam imaging system as well. That's really important. It's got an inbuilt mass filter, a Wien filter, E cross B, of exceptional resolution. So what this lets us do is actually select isotopes to dope, not just atoms. And that is absolutely critical for what you'll see. It allows us to do resolutions below 20 nanometers for ion beams. That's a real challenge, but we've managed to do that. The energy that the ion goes in determines how deep it goes. And for our quantum computer, we need to be able to talk to the ion, to put the data in. So you don't want it too deep. And so these energies here were felt to be sufficient. And as I say, if we want to put a single atom in, we need to be able to dope it with one atom and know we've put it there. But also, I'm going to show you some work on purification. So we need to actually do material synthesis effectively in this. And actually, what we've done also is work out ways of how we can harness this system. This was part funded by Royce, with the other systems Leeds, and elsewhere in the UK, Nottingham, and elsewhere. So we can deposit materials and transfer them under vacuum to this tool, breaking, do deposition, do doping, take them back, do more deposition. And that's a really important capability. And down here, this periodic table I thought it was up to date when I sent it to Lucy, and then I got an email half an hour later telling me we got another new source. But this demonstrates in red all the different species we can now dope with this tool. And prior to us doing this work, typically you could do gallium, which everyone knows about. You could actually do some lithium and gold, but not really much else. So we've really taken the field forward by giving access to all of these different materials. And I'll show you some of the applications of those later on. Okay, right, so what's the first problem we need to address? We're going to use silicon as our host, and we're going to put our atom in there. And here's a picture of our atom in the middle here. This is a phosphorus atom with its electron spin, and it's sitting in this crystal. The problem is, in our crystal, not only do we have silicon-28, the isotope silicon-28, we've got some silicon-29s, which are these red ones. And this is drawn to kind of scale. And also we have some silicon-30s, which aren't as problematic, but do cause some problems. And what's the implication of this? Well, these silicon-29s have a nuclear spin. And this nuclear spin can interact with the electron spin. So you may be aware of Schrödinger's cat experiment, where is a cat dead or alive, and if you lift a box and you look at it, it has to be one or the other. If you like, you can consider the nuclear spins as they move around being like you looking at the cat. So what it causes is our electron spin to lose that quantum property, that entanglement, and it collapses, and so we can not use it anymore for quantum computing. And how we measure that is in something called the T2, the coherence time. And if I take this solid line here, this is natural silicon with its about 4.7% silicon-29, and it means we have a coherence time of under a millisecond. So that means you have less than a millisecond to do all the quantum calculations you want to do before you can't use it anymore. Okay? That's not good, right? You can't do a lot in that time. But what this blue line shows, this is modeling, if you reduce the number of these silicon-29s, then you should increase your coherence time up here. And that is a challenge. Can we create a silicon system which is pure enough to allow us to do scalable quantum computing? So, what have people done? Well, we know that you probably could do this because there was a project called the Avogadro project by the world's metrology labs, which was trying to build the world's kilogram standard. And so here, held in someone's hand, I'm sure it's no longer a kilogram because it's covered in hand grease and other things, is a 1 kilogram ball of silicon, which was polished very carefully, made around the world, and little bits of this kilogram ball came from here, and of course there's other bits of silicon in here, right? And so these little chips of this amazingly pure material is scattered around the world in labs, and fundamental research has been done on these, and yes, you know, if you use this material, these coherence times are much longer. So why don't we use this? Well, the problem is the cost of creating that ball was about $3.2 million and took a long time. That's not a scalable, affordable technology. Right? So we need to find an alternative way of achieving this. So what do we do? Well, we've got this implantation tool. And so we can fire ions down, and we can choose silicon-28, for example. And if we choose the energy just right, and this is now wrong, but we haven't published a work showing the correct thing. Until it's published, I can't tell you what the exact energy is you need to use. But the theory was, if you use 40 keV, for every one silicon-28 going in, you knock an atom out. And over time, you're going to knock out some silicon-28s as well, but also 29s. So gradually, you're going to enrich your material and make it purer and purer. So that was the theory. And so because we had the tool to do that, we started working on it. And here's an AFM image of a region. And this region here, where you can see it's raised, is where we've done the enrichment with silicon-28. The black squares, where we've done analysis using nanosims later. So that's what they're there. This scan is showing the fact we can choose silicon-28 over silicon-29 and 30 quite accurately. So we did this. And in this region here, we've put about 1 × 10⁻⁹ atoms of silicon-28. That's a very high dose. And this took about 17 to 23 hours, depending on the current we use. It takes a long time to do a 20 micron square. But in that 20 micron square, we can easily put 100,000 qubits if we needed to. Right? So the real estate is fine. Okay, so we need to look at our material now. We've done this enrichment. What does it look like? Is it really enriched? Is it crystalline again? What's going on? And so what I'm showing here is a TEM image of the interface, the end of range it's called. So we're implanting from the top downwards, enriching. And as we go in, we knock ions out, but we also smash up the lattice, and we make it amorphous from crystalline. And this shows interface. So above this interface, no diffraction pattern. Thank you, Bragg. Helps us do this sort of work. Below the interface, end of range, beautiful diffraction pattern. So these are single atoms of silicon. These is an amorphous mess of silicon. So that showed us that we enriched all the way down the material to this depth here, which was a few hundred nanometers. So easily deep enough to host our qubits. Okay, we then have to recrystallize it because we need to put our dopants into a crystal environment. We do that through heating, and we have recipes for doing that. And here's another TEM image. And these dark patches here are the end of range, so they are equivalent to this point here in the sample. And so if we look above that, right to the top, beautiful recrystallization. So these are single silicon atoms. Below, yeah, single, so that's the same. And these are looking at these end-of-range defects, and there's some twinning in there, which is all very interesting if you're a crystallographer. So we've managed to enrich the material. We've managed to recrystallize the material. What is the level of enrichment? So to do that, we turn to a different technique called nanosims. So we're now destroying the sample, ripping off the atoms, atom by atom, and measuring what it is, effectively weighing them. Are they silicon-28, 29? And from left to right, this is the top of the surface, and this is going into the sample. And at the top here, I'm showing this is the signal you expect to see from natural abundant silicon-28. So deep in the sample where we haven't enriched it, that's what we get. But as you get close to the surface, the silicon-28 goes up really high. And if we look at the silicon-29 and 30, it drops down massively. And if we zoom in again and look really close, we can actually measure the concentration of silicon-29 in that region. And in this particular sample, we get down to 2.3 parts per million. This is remarkable, and I'll show you where it sits on that plot in a minute. Also, though, we look at other things like carbon and oxygen, because previous techniques, as they were enriching, also intercalated carbon and oxygen, which have also bad effects on our length, our coherence time for these qubits. But we find that we haven't included any of those. So we keep the purity of the silicon in there. And if I now match up this nanosims profile, I've turned it sideways, so depth is coming down, with the TEM, you can see that at about 50 nanometers, this region here, which is exactly where the energy of our implantation is, we have the highest enrichment levels. So this all looks good for doping. Where does this lie on this plot I showed you earlier? So remember, natural silicon is in red with our less than millisecond timescale. And I've shown some other work of other people doing experimental stuff, including our colleague Dave Jameson's group in Melbourne. And they managed to get down to 0.1 T2s. Avogadro, that big ball, that's what they'd managed to produce. That was the world's purest silicon until we published this work, and we're now here. So we've fundamentally shifted and addressed a key challenge for making a scalable silicon quantum computer, right? So that's the number one of the first 3 easy steps to make a quantum computer done. But we have that now, so that's really positive. Okay, right, what's next? Next, we have to put the qubits in there. And I want to put 1 qubit in, for argument's sake, not 2. I want 3 atoms next to each other, because they'll all interact and it'll be messy. How do we do that? Well, what we do with our tool now, rather than putting lots of ions in, we're going to turn the current right down, and then we're going to chop the pulse. And that's what this is showing here. So beam closed, open beam for a short period of time, close it again, and during that time, we're going to look and detect, did an ion go in? And our original detection looked something like these curves here. So you see there's one in gold, which is a single ion event, and then there's one in black showing where 2 went in, and we got 2 peaks. That was a bit clunky, and this was, we've now refined it, and underneath it, this is now a new detector, so much more resolved. So effectively, we can count in the atoms. How good are we at doing it? Well, it depends on the atom we're using and the material we're going into. But 87% would be a low efficiency. Some materials are up at 95%. Our aim is to get up to 99%. But this is still way, way better than what you would get if you just used random single ion doping with Poissonian statistics. So that's how we're going to count in our atoms to create the qubits. Okay, and here's a scan of many of these things. Here we've set the average number of ions per pulse to about 3 or something, and you can go in and we can count them. That's what we see. Okay, so have we managed to do this? Well, here's some fantastic work which we showed. So here we've implanted antimony ions, and here you can see single antimony atoms in silicon. What's nice about this, and a bit surprising, because these samples haven't been annealed, is that each antimony atom is sitting exactly on the lattice site, and there's no damage around them as well. So we're doing a piece of work at the moment to understand why that occurs. Why are we seeing no damage? Is it because they get annealed effectively by the beam when we're doing the imaging? So we've created antimony, and actually, occasionally you see some that are quite close together, and I'll come on to that in a minute. Right, so how close? If we're going to make 1 million qubits, then ultimately we have to control the qubits and entangle qubits with each other. And so the initial proposals on this scheme was that we had to have the dopants 20 nanometers apart, hence our resolution of our tool being 20 nanometers, so we can put them in. The world's moved on a long way since then, and we now have these flip-flop qubits. So what you can do, you can place an ion here and an ion here, and then you apply gate bias at the top, and you pull your electron up. So this is your electron cloud, your single electron. And then actually you can then pull that electron across here and entangle it with this one and send it back. And it turns out you can do that over quite large distances. And here you see some simulations of this electron cloud being totally pulled off its home atom, so you can entangle it with something over here. And you can do that over hundreds of nanometers. That really relaxes the constraints, because if you have your qubits hundreds of nanometers apart, then all of your electronic controls are much easier to insert and put in, because the fabrication we use for transistors in standard CMOS is on that level already. So that helps us do that. So I talked about this nuclear spin being a problem in silicon-29. If we have nuclear spin in our qubit, it's actually an advantage. And here's some really nice work which was shown recently by our collaborators in the University of New South Wales, where they use an antimony. And if you take antimony, 1, 2, 3, this are its nuclear states. So each of these can be a different quantum state. So rather than being 0 and 1 at the same time, you can actually mix all of these up at the same time. And then if I mix into these, the electrons spin up and down, you end up with this 16-dimensional space in which you operate. Okay, now, why is this an advantage? So if you remember, we had antimony, single antimony atoms in here. And so here I'm doing a plot which shows if I just take a two-dimensional system, so a phosphorus qubit with up and down, and I use it instead, I use antimony, then if I follow this orange line here, 1 million standard qubits can be achieved with about 120,000 antimony qubits. That's a massive reduction in the scaling challenge for doing that. If, however, I now start using pairs of antimonies, which we can actually put in, then I'm on this line here. And you see I get the same benefits with 64,000 qubits as I would with 120,000 single qubits or a million qubits. So this is addressing the scaling challenge too. Okay, what else do we do in the last few minutes of my talk? So I said we do some work on diamond. Here's some work we've done with Dorian, Meta, and Jason, Oxford and Cambridge. And here we're putting in tin into diamond deterministically. So you see we're making arrays. These are arrays of single photon emitters. Here's a G2 showing the single photon source. We can turn these on and off by laser annealing. Here's the low temperature single photon emission lines. Beautifully separated, exactly what you expect. So this is another alternative mechanism, but also, I can see you behind me, yeah, important for quantum. I've got 2 more slides. I'll very quickly go through. Secondly, for those interested in photonics, lithium niobate, a very nonlinear material required for switching of light, etc. Very difficult to dope. We've managed to dope that with erbium and get erbium emission, which is technologically important for communications. We don't just do this, though. We do work with this tool for many different areas. This is a study recently we've done on nuclear reactor-grade graphite, implanting with cobalt and looking at damage mechanisms in that. So this tool is really very versatile. And what's next? Well, scaling. So we've recently got funding from EPSRC to do the next generation tool for scaling. So rather than taking 17 hours, we can do it in 17 minutes, the enrichment. And also, we're grateful we got funding led by Leeds for some dilution fridges. So there's going to be a Northwest dilution fridge system for gigahertz to terahertz characterization. So that's some of the things which we're heading on to. And with that, I'll stop there. You can use the QR codes to get papers and things. So it's me being, dragged into the electronic age, Edmund. And with that, thank you.
Yeah, thanks, Richard. That was really brilliant. We have a couple of minutes for questions.
Right at the back. Yeah.
Right.
Thanks, Richard. That's really impressive development. I'm curious about, you mentioned this with regards to the antimony, that you didn't see any damage, but I would have thought for the silicon, with the amount that you're putting in there, that you would have created other problems like vacancies and interstitials. Those somehow don't interfere with the performance?
So for the single atom ions going in, we don't see any of those. We did see that in the enrichment. So that end of range, if we go back to a TEM, where was it? So here, these are interstitials and things at end of range. They're 200 nanometers deep, way, way away from where the qubit is. So they're irrelevant, right? And that's what you expect.
Why don't they form up above? Is the energy enough to anneal them while you're...
Sorry, I can't hear. Sorry. Yeah.
Why don't you get any of those up in the enrichment layer? So just enough an energy that
epitaxially regrown, recrystallized with the
I see, recrystallize it. Okay.
So we come all the way up, and that's why we don't see any of those. Yeah. Edmund at the front here.
Sorry, Richard. You talked about the tool and the wide variety of ion species. So I think a question maybe for the audience, if people had materials they would be interested in implanting with ions, in particular deterministic implantation, can they do it? How would they do it? What would be the mechanism?
Yeah, so here's our current list of ions we can put in. I need to add nickel to this, apparently. That's a new one that we've got. If you're interested in using it, send an email to me or actually to Maddie. I'll send it to her. And we have a conversation with you. So access, it can be through Royce for initial work. You can get funded access for this. If you need an iron which isn't in red on here, again, have a conversation, because some are very easy to make, and there's a bit of extra cost for doing that, but we can sort that out. If anybody wants, I don't know, cesium, right? I've already set fire to one implantation line in history with cesium. I'd rather not do that. And likewise, if you want radioactive species, we're not going to do that in this tool. But if you've got $1 million, actually more than that, it'd be about 100 million, we can build you a radioactive version of a tool for hot iron implantation too, which is very interesting and is being considered, actually. Yeah, so come and send me an email if you're interested.
One more up here. No?
Oh, there's one in the middle.
Thanks, Richard. Very inspiring stuff. Can you comment upon your new tool that you're developing that's going to be able to do this in a much shorter timescale and how it's different from the old tool?
No. It'll be quicker. So it'll have the same capability, effectively. Clearly, if you do something quicker, you need higher doses, higher flux rates for it. The technology behind it, obviously, can't discuss. We will be looking, though, we're going to get 2 new tools, actually. And what I can say is one of them, we're going to start, the number of parameters in operating this tool, we calculated is about 23 different parameters. So optimizing its operation is a real challenge, and that's where machine learning and AI can come in. So it will be a piece of work around the use of that in one of it.
Okay, thanks very much. Just before we let Richard go, I think Edmund has something.
It's not a hat.
Not a hat. So we told you, Rich, you were allowed 25 minutes, and that was 30 seconds. 30 seconds for each year of life, or something like that. I think if I got the right calculation here. We thought we couldn't just send you away from Leeds and something. Of course, we're being very economical in the university with things like packaging, so we thought you'd like a bag, that we had plenty of spare bags here. So here's a bag for you. And we thought we'd like a little bit of local lubrication as you go home. And there's been a consultation with your group behind the scenes who seemed very uncertain as to what the right thing would be. But from us at Leeds, thank you very much, Rich, and particularly on this day to come over and speak to us. So thank you very much indeed, Rich.
Thank you very much. Shake hands. I was going to shake hands with you. Thank you. Thank you. Right.
Yeah, thanks. That was terrific. Okay, so our next speaker is Zhilun Liu. He is from the University of Leeds in Materials Science and Engineering. He's Associate Professor in Materials Science and Engineering in the School of Chemical and Process Engineering. He did his PhD in Sheffield, where he won the High Quality Thesis Prize. Then he's been to Germany, back to Sheffield, then Edinburgh, Napier. Now he's here in Leeds. We're delighted to have him here. His work focuses on structure, composition, property relations of lots of different functional materials, but today he's going to tell us about his research on electroceramics for dielectric energy storage. So please, Zhilun.
Thank you. Thank you. First, thank you, everyone, and thank you for the Bragg Centre to organize such a fantastic conference and definitely invite me to give a talk. We're happy about this. Yeah, my topic today will be based on the electroceramics because I did this from my PhD. And electroceramics had many different applications. Like today, I will show you about dielectric energy storage and also the thermoelectric energy harvesting. And my research now mainly focus on different parts, from materials to physics, such as these 2 topics I will give the presentation today. And also I'm doing quite a lot of inelastic neutron scatterings For example, for fast-trating magnets, for quantum spin liquids, and also I have some collaborations to use in elastic neutron scattering for the phonons. So the phonons is very important for some electric materials and quite a lot of other materials. Okay. Today, the first topic I would like to cover is dielectric energy storage. First, so everyone knows capacitors is very important electronic components, okay? And then the conventional components, they look like that. So we have two layers of metals, and inside we have the dielectric layers. You can use a ceramics or use a polymer materials. But however, the most used and produced capacitors is a multi-layer ceramic capacitors. So normally they look like that. So you have many MLCCs in your mobile phones and computers in modern electronics. And they have quite a lot of advantages. The most important is that they have a high power densities and also fast charge and discharge rates and very high operating voltage and very reliable. Normally you can use many years. But however, based on the picture on the right-hand side, you can see compared to the other conventional energy storage, everyone knows the fuel cells, batteries. Someone maybe know the electrochemical capacitors or supercapacitors. We call these traditional capacitors. They have very low energy densities. So normally they didn't use for energy storage in previous years. But now recently, because of the development of the technology, so we can increase these energy densities significantly. So that's why we try to increase the energy densities closer to the batteries or supercapacitors. And try to let you to understand what's the difference between power densities and energy densities. Here I use these pictures. So for example, if the materials have very high power densities and low energy density like the cup, so you can pour out the water very quickly, so it means it can charge and discharge very quickly, similar like the capacitors. And the bottles is similar like the batteries, so you can store quite a lot of energies, and then, but you cannot pour out very quickly, so they cannot charge and discharge very quickly. And also here, I would like to emphasize again, there's normally quite a lot of misunderstanding based on this dielectric energy storage and the other types of energy storage. So for the supercapacitors, batteries, or fuel cells, you have the chemical reactions like at least the lithium or sodium or the hydrogen need to move inside, and then to convert the chemical energy to the electricity. But for the traditional dielectric capacitors, it's just based on the distortion of the electrics and other type of things. So that's why they can charge and discharge very quickly. But however, definitely the energy density is lower than the batteries. So the key things is we have some new requirements to increase the energy densities. So what's the meaning of higher energy density? So it means these capacitors, we expect we have larger capacity and higher operating voltages. And definitely small size in the same volumes. So compare the conventional vehicles and the current hybrid electric vehicles or hybrid vehicles or electric vehicles, we need quite a lot of higher quality multi-layer ceramic capacitors. So that's why dielectric energy storage is important now. And in the real case, I already showed they looks like that in your computers or mobile phones. Definitely, in the real applications, we have many other parameters we need to care about, like the temperature coefficient, equivalent series, capacitance tolerance. But in research, now we just try to focus on how to increase the comprehensive energy storage properties first. Okay, and here I would like to go back to the very simple math to how to calculate the energy stored in the capacitors. So if we have these parallel capacitors, we can calculate the capacities, and finally, we can calculate the energy stored in these capacitors. So normally, these related to 4 different parameters. So the first two is the area, A, okay, so, and the thickness, D. So normally, definitely, if we would like to keep the volume as the same, so we cannot normally change the area. But for example, supercapacitors, you can change the area, like use the carbon nanoparticles or something to increase the roughness of this surface, and then can significantly increase the area. But for the dielectric capacitors, normally we didn't touch the area, we only changed the D. So that's why we have multi-layer ceramic capacitors. In the same volume, if you can make more layers, and then you will significantly increase the energy stored. And definitely, we can manipulate the materials. The dielectric materials, definitely, we would prefer the dielectric materials to have very high permittivities, okay? And then they can operate at very high voltage. And this is for the capacitors. And for the materials, so normally in research, we have this we call the P loops, hysteresis loops. And then the x-axis is the electric field we applied for the materials, and the y-axis is the polarizations for these materials. So normally, this area, this purple area, so it related to how many energy can store in these materials, and this area is a loss area. So we have the maximum polarization, minimum polarization, and here this is the maximum electric field we can put in these materials. So all these parameters are very important for the energy storage dielectric materials. So that's why based on this, we have normally can categorize materials for 5 different types. So for example, the linear dielectrics and the photoelectrics, ferroelectric, relaxer ferroelectric, and antiferroelectrics. So simply based on their P loops, definitely, you will see the relaxer ferroelectric and antiferroelectric, they have the higher chance to have larger area here. So it means they have higher chance to have higher energy density. So that's why later I will introduce these 2 material systems. One is a bit based on bismuth ferrite, strontium titanium, relaxer ferroelectrics. Another one is based on the silver niobate antiferroelectrics. So for the bismuth ferrite-based materials, so first I choose this 0.6 and 0.4 strontium titanium as a starting point because this is a nominal methotropic phase boundary. So it means around this phase boundary, we have the higher chance to have the very high maximum polarizations. So, and then I add this bismuth manganese niobium, BMN, to try to reduce the polar couplings, and then it will lower the dielectric loss and also increase the efficiency. And the strategy is like that. So if you did some research related to bismuth ferrite materials, you may know this materials has very complicated conduction mechanisms, like have the ionic conductions, have the electronic conductions, and the electronic conductions normally is a p-type for the bismuth ferrite-based materials because when you're heating up and cooling down to make the ceramics, definitely you have some oxygen vacancies, and the ion can change from valence 2 to valence 3, valence 4, and then also you may have some bismuth loss during the heating and cooling. So that's why first you need to understand the conduction mechanisms for the bismuth ferrite-based materials first. And then use a different doping to try to decrease the electrical conductivities, and then use the different N members like the BMN to reduce the polar couplings. Finally, use a tape casting to make the multi-layer ceramic capacitors to optimize the energy storage properties. So these are normally the strategies we use. We manipulate the electrical properties and also manipulate the microstructures. Definitely, you will need to have the high density ceramics and smaller grain size, etc. And finally, make the multi-layer. And also here, I would like to briefly introduce many speakers, they already mentioned about impedance spectroscopy. So impedance spectroscopy, this technology is very useful to investigate the electrical homogeneity or electrical heterogeneous materials. Okay, so for example, if you see one semicircles in this Z star peak, Z star box, and then one Debye peaks in the Z double and M double prox, we can assume these materials only have one electroactive regions. It equals to one parallel RCA elements. And then it means at this point we can say it's roughly electrical homogeneous based on the resolutions of the impedance spectroscopy. And quite a lot of different research, if you see a not very typical semicircles and then more than 2 peaks, maybe one peak here, and then you can observe the separations of like the grain boundary effects or the grain effects or the electro effects. This is also very popular for the battery and the fuel cell research. And okay, so the first data set is I do the impedance spectroscopy based on the original 0.6 bismuth ferrite, 0.4 strontium titanate. And I found out 3 take-home messages. The first thing is that it has electrical heterogeneous because you see there's 2 peaks here, and this semicircle is not very typical. It's quite wide. And also the activation energy is quite low because I mentioned we have the oxygen vacancies, etc., and high electrical conductivities. And when I compare the material sinters in air and nitrogen, so I find out it's a p-type electronic conduction. Okay, so now we know it's a p-type electronic conduction, so I can use a donor doping to significantly reduce the electrical conductivities. And based on the Seebeck coefficients and the data, we can see the conductivity reduced quite a lot. And also the electrical homogeneity increased. So now after the doping, the sample only have 1 typical semicircles and the Debye peaks is at the same frequency. So it means now we got the electrical homogeneous dielectric materials. And I find out 3% is the optimized concentration. And then after that, okay, we got very insulating materials, and I used the BMN as an end member to put in the BFST to reduce the polar couplings. So based on the LCR data, we can see this peak become broader and broader, so it means they have more relaxed behavior here. So I find out 10% is the best concentration. And then we got very high energy densities based on these ceramic samples. And now we got the ceramic samples, and then we make these multi-layer ceramic capacitors. In the lab, first we just use a platinum. Platinum is very expensive. Normally in the industry, we need to change the electrode, like the nickel and copper in the future. And then decrease the dielectric layer thickness to 8 micron, and then got a very high energy storage density. And normally, how we make the multi-layer ceramic capacitors in the lab, so we use a ball milling to mix the ceramic powders, use the solid-state reactions, and then use a tape caster to make a very thin ceramic films, and then use a screen printing to print the electrode on top of it. And then after that, we cut it to different pieces and laminate them 10 layers or 20 layers, and then use a hot pressing to press them, and finally put it in the furnace to fire them, and then we got something like that. This is what they look like in the real case, but in the industry, we have more, a little bit more steps compared to in the lab. Okay, so this is the first based on the bismuth ferrite strontium titanate relaxer ferroelectrics, and the second one is based on the anti-ferroelectrics, so silver niobate based. Oh, sorry. And yeah, here I will just be quicker. So this one, I use co-doping, neodymium and tantalum co-doping to try to reduce the polar couplings and conductivities. So finally, the story is we use in situ synchrotron X-ray to analyze the data. So we see no electric field. We have the central symmetric space group. So that's why the polarization is nearly 0. But however, at high electric field, so we put this electric field, and then we have a non-central symmetric space group, and then that's why we have this ferrite configuration to have very high polarization. Sorry, I think maybe I put too many things. Okay, I will do this quickly. For the thermoelectric materials, it can convert heat into electricity and vice versa, simply speaking. I have many applications. Okay, and then in the markets, now we have quite a lot of toxic and naturally material elements for the thermoelectric applications. So that's why in my research, I try to use oxide materials for the thermoelectric applications because they can survive at very high temperatures, and this one only survive at lower temperatures. And then I just choose the very textbook-like strontium titany, use a lanthanum-doped strontium titany to increase the thermoelectric properties. So that's why I choose 3 different nominal doping mechanisms. So the key things is try to introduce quite a lot of vacancies to decrease the phonon scattering, increase the phonon scatterings, lower the thermoconductivities, and increase the thermoelectric properties. So finally, I find out A side vacancy is the best. Okay, so why is the best? Because of these 2 equations. In the given PO2, these A side vacancies will facilitate removal from the lattice oxygens. So finally, I got the very high ZT values based on the thermoelectric oxides, and then use a TEM to analyze. They have different octahedral tilting systems, and combine it with the A side vacancy, and finally deduce the modules to try to understand why this material has high thermoelectric properties. Okay, so these are conclusions. These works provide the energy guidance, engineering guidance for the electroceramics used in different areas. And I would like to thank all the collaborators. Okay, thank you very much for your attention.
Okay, thank you very much. We can maybe take 1 or 2 quick questions, if there are any in the audience.
So with trying to store so much energy in these systems, do you sort of look at, do you see degradation over a period of time? Do you sort of do lifetime testing of them and see, if you cycle them, what will happen a week later, a month later with those materials?
So you mean the dielectric one?
Yes, yeah.
Yeah, the dielectric one, as I mentioned, is very, very stable because, I did the cycles, is many 100,000 cycles, and because this dielectric material is very frequency stable, and also the cycle, the fatigue and cycle is stable. So that's why compared to battery materials, they are totally different. Yeah, because battery materials, if you use for the long term, definitely limited by the chemical reactions, normally you have some degradation. But this one, we don't, the traditional one, we have nothing to degrade nearly. Only the loss is from based on the. Only the loss is based on this inside this P loop, the loss, the efficiency. So that's why after 100,000 or even 1 million cycles, they are still stable. They can keep the, yeah. Thank you.
Great. Okay, let's thank Zhilun once more. And so our third and final speaker this morning is Nathan Fox. He's from the School of Electronic and Electrical Engineering. I think he did his master's degree in physics, it says here, and became fascinated by condensed matter physics, and who wouldn't be? And so he did an internship on topological insulators, and that has now led on to his PhD with colleagues in my group in physics and the School of Electronic and Electrical Engineering. Anyway, I'm delighted to welcome him to talk about his work in his PhD on topological insulator metamaterials for plasmonics. So yeah, please, Nathan.
Yes. Is this working? Yes. Thank you for the introduction. Today I'm going to be talking about, as you said, my work on topological insulator metamaterials for plasmonics. Perhaps if you're sat there, you'll be like me in my undergrad, asking yourself, why should I care about insulated materials when there's so many fabulous, superconductors or what have you? So my aim in this short presentation is to convince you that topological insulators are interesting, and then give you a bit of demonstration of what I use them for. So first, we're going to start off with a recap on classical metallic conductors. So I've got my very nice diagram over here. This is copper. You can tell it's copper because I've made it this nice brown color. And then we've got positive ions surrounded by a sea of delocalized electrons. And these electrons are going to allow us to carry our charge through the metal, giving us conduction. So conversely, we have the topological insulator. So this has no positive ions or electrons. It actually has an insulating bulk band gap. So there's no allowed conduction states in the bulk. However, because of quantum effects caused by strong spin-orbit coupling, on the surfaces, we're going to have highly conductive states. So perhaps, hopefully, unlike me in my undergrad, you've not been tricked into thinking that these are truly insulating. So these states have some very interesting properties. Firstly, they're highly conductive, and they're in fact protected from backscattering, which gives them a very low energy loss. So this is a very similar behavior to a more famous material, graphene. But unlike graphene, we also have this spin momentum lock-in. So if we look at my two diagrams here, this is real space and this is reciprocal momentum space. You'll see that when we have a particular momentum, we're going to have a corresponding spin that is locked. And then if we want to reverse that momentum, we are going to have to flip the spin as well. So this gives us some very interesting applications in the fields of like spintronics. Okay, so if we want to use a topological insulator, sadly, we can't just go to the supermarket and buy some. But we are very lucky that on the ground floor of the Bragg building, we have the Henry Royce Institute's molecular beam epitaxy system. So this is an ultra high vacuum deposition system where we can evaporate our constituent elements onto a substrate and grow our material layer by layer. So these elements are going to be bismuth and selenide for the bismuth selenide topological insulator that I use. And then thank you to the condensed matter group who've done lots of work optimizing this so that we can have very high mobility, very uniform samples that are perfect for fabrication of devices, which I use in my work. So my field of study is plasmonics, so that's the generation and observation of plasmons. So what is a plasmon? Well, simply it's a collective carrier oscillation. So if we have all our carriers sort of joined by a tiny little spring, and then we vibrate one, that oscillation is going to travel through our system. So here we have a simulation on the left, and we are perturbing the electric field on the left side of our topological insulator, and then we can see the plasmon is propagating through the system. So if we want to reproduce this in the lab, we're going to need a source of alternating electric field, and thankfully that is simply light. So quite easy to reproduce, but as we start to explore these higher frequencies where things start to get a bit more exciting, classical materials like gold, for example, are going to become quite lossy, whereas our topological insulator, which we've said has low loss, can sustain these high frequency plasmons. If we want to excite our plasmons, sadly, we can't just shine light directly onto our system. That's because momentum is not conserved in the photon absorption process. So actually, if we look at my dispersion relation here on the left, you can see, so this is just frequency versus momentum. Our photon has a very linear relationship, but then our carriers in our topological insulator have a non-linear relationship. So we're going to have to try and give them some extra momentum to allow this absorption process. And to do this, we're going to pattern our devices with sort of sub-wavelength structures, and the interactions between these structures are going to give us the extra momentum we need for photon absorption. So here's another simulation. This is the X and Y component of the electric field. And you can see that we were actually localizing our plasmon inside the structures, creating a standing wave with sort of areas of enhanced electric field at either end. Now, if we actually want to create some of these devices, once again, we're very lucky. In the basement of the Bragg building, we have the Leeds Nanotechnology Clean Room. So this is finished in 2021 with all state-of-the-art equipment and processing bays we need. And most importantly, it has a very precise environmental control. So this is the temperatures for our chemistry, but also it filters out all the dust and debris from the air, which when you're landing on very, very small nanostructures can completely ruin the device. And here are said nanostructures. So on the left, we have a ribbon array, and on the right, we have a disk array. And so for a sense of scale, these are 150 microns high. So that's approximately 2 human hairs, I think. So exceptionally small. And then finally, once we've created our device, we've predicted what's going to happen, we need to generate and measure these plasmons. So how we're going to do that is with some equipment that we've made in the terahertz lab at the top of electronic engineering. So this is the terahertz time domain spectroscopy system. And this lets us fire pulses of terahertz radiation through our sample, and then we measure what terahertz is allowed through, what has been stopped, and that gives us a picture of the dielectric properties of our material. So if you look on the left, for your right, first we have the plain thin film, which sort of has 2 characteristic absorptions. So this is the Darude response from the free carriers, and then also this phonon peak. So a phonon just being a fundamental vibrational mode in the material, but this is quite useful for letting us observe this plasmon. So we'll see that as we pattern the device with a ribbon, we're actually going to start shifting this phonon due to the interference with the plasmon. And actually, when we get down to 2 microns, we've completely renormalized the optical behavior and removed this phonon. And then you can start to see the shoulder of the plasmon just here. So we've demonstrated that we can generate plasmons. So finally, looking to the future, we're going to want to control these plasmonic devices and utilize them in devices. So firstly, we're going to be looking at applying electrostatic gates. That lets us apply a voltage bias to our sample and then alter the electric properties of the carriers directly, but then also reducing the dimensions of our structure even further through use of more advanced photolithography techniques like E-beam photolithography. So going from micrometer resolution down to nanometer resolution. And this lets us explore not just the optical plasmon, which we've been looking at, but the acoustic plasmon, giving us access to spin currents in our device and then extracting those to other materials like antiferromagnets. So thank you for listening. I'd like to thank you. Cheers.
Just take the applause.
Yeah, I'll just take it.
Okay, we have time for a couple of questions.
2 quick questions, actually. On one of your slides, I saw a temperature of 6 Kelvin.
Yeah.
Can you comment on whether this high conductivity you may have in your sample, your properly patterned sample, but this also would occur at room temperature?
So the surface states should be robust to room temperature. The problem is there are some bulk carriers in the material. So these start to obscure the behavior a bit at these high temperatures. So yes, there should be plasmons at room temperature. Is it easy to see them? Not quite as easy as it is at low temperature.
It was more about the application. If you could use the high conductivity at room temperature.
Yeah, I think...
It's more than physics.
Yeah. With the optimization that condensed matter is doing, with sort of implanting different ions to reduce these bulk carriers, I think as this improves, the temperature applications will also improve. So I think in the future, definitely higher than 6 Kelvin, but I cannot say for certain how high.
Excellent. The other quick question is, did I get this right that the material you're depositing is bismuth selenide?
Yes, yes.
Okay, thank you.
Thanks.
Okay, maybe I can have a quick one. So you talked about spin momentum locking, and right at the end, you mentioned spin currents, but in between, does the spin play any role the spin momentum locking in the form of the plasmons, or are they
I mean,
conventional plasmons?
apart from the obvious protection from backscattering that gives you the low loss, the spin has little effect on the actual dielectric properties of the material. But if you put in a magnetic field and break the time reversal symmetry, you'll lose the surface. So
would you expect sort of different plasmon properties?
Yeah, I think you'd lose your mobility and then struggle to sustain the plasmon.
Right. Okay. Right. Let's thank Nathan once again.
Okay, let's try that one again. So I'm Fiona Meldrum from the School of Chemistry, and I'm going to be chairing the next session, which is on multi-scale materials. So again, we have 3 speakers. My great pleasure is to introduce our first speaker. So we have Professor Pratibha Ghai from the University of York. So her particular expertise is in transmission electron microscopy, where she has really pioneered the development of environmental TM. So rather than the traditional high vacuum environment, she's interested in looking at samples in a real environment like gas. So she has also gone beyond that and looked to looking at the real reactions in environmental conditions, so particular emphasis on catalysis. So Pratibha has been awarded many prizes in her career. Notably, she became a Fellow of the Royal Society in 2016, and she was made a Dame for her contribution to chemical science and technology in 2018. So it's my huge pleasure to introduce Pratibha, and I'm sure we're going to have some wonderful images to look at.
Okay. Well, thank you very much for that kind introduction. Can you all hear me at the back? Okay. Good morning, everyone. First of all, it's an honor and pleasure for me to be here at this fantastic conference. And this is the title of my presentation, Visualizing Single Atom Dynamics in Chemical Processes. I'm going to explain all that in a minute. Atoms are telling us, catch me if you can. So we have caught them by advancing the frontiers of dynamic electron microscopy. You've seen a lot of electron microscopy data here, but they were all done at room temperature in vacuum. But today I'm going to take you to the world of real reactions and how we can image them. Okay, my co-authors are Ed Boyce, who is here, Alec Lagro, Thomas Martin, and Michael Ward. We are from the University of York, and we also have association with the University of Cambridge. These are our funding agencies. Main funder is the EPSRC or the UKRI, and we also have funding from UK companies, as I'll mention later, and also some from the University of York. But before I begin my talk, I would like to thank Dr. Andrew Lee for the kind invitation to present this talk, and thanks also to Helen Walters for all her support, and thanks to our key members who are from different countries who have contributed a lot. Without their contributions, the work would not have been possible, and also funding agents, as I mentioned, and we have collaborations with Catalyst Technologies like Johnson Matthey and BP, and thank you all for being here. So basically, I'm going to talk about dynamic in situ electron microscopy instrumentation that we have developed to look at reactions as they take place and impact in chemical sciences, and also applications to chemical processes and catalysis, and then I'll finish off with some conclusions. Okay, I know some of you may not be familiar with chemical processes and catalysis, so I have a couple of introductory slides here. First of all, chemical processes are speeded up by materials known as catalysts. So this speeded up chemical process is catalysis, so that's what I'm going to use the word catalysis. Basically, this speeded up chemical process, and the catalyst can be solid metal oxides or metal particles. And catalysis is central to the global economy and industry. For example, more than 90% of our chemicals and energy sources come from catalysis. You can see that. And it provides up to 40% of the world GDP. All other technologies put together make up the rest. So you can see how important it is. It puts many trillions of dollars into the global economy and billions of dollars into the UK economy. So it impacts heavily on our daily lives. All our energy, food production, healthcare products, housing materials, chemicals, climate control, they all come from catalysis. And many catalytic reactions involve gases catalyzed over solid surfaces. So we call this heterogeneous catalysis. So I'm going to talk about gas-solid reactions today. As I mentioned, these can be supported metals or metal oxides. And most importantly, these gas-solid reactions take place at the atomic level. Okay, so we need to understand them at the atomic level. We need to understand the dynamic atomic structure property relationships, which are the central to catalytic process. I tell my students, when they are on the beach, they need to look at the sand particles, not just the beach, because by understanding the sand particles, they can figure out how the beach is made of. So it's exactly the same principle. By understanding the fundamental atomic level reaction mechanism during the reaction, we can begin to understand how the processes work. And so basically, we need to visualize and analyze catalysis at the atomic level in real time, and that's crucial to insights into dynamic atomic processes, which can help us to develop better materials and sustainable processes. And increasingly, it's believed that dynamic single atoms and clusters of atoms are important, but what they don't tell you that they can also contribute to degradation, which I'll show you later on. So we have to be quite careful. And I worked in industry before some time ago, and practical large-scale catalysts always contain a mixture of single atoms, clusters, and nanoparticles. So we need to understand the relationship between all these three during the reaction. However, although catalysis is so important and takes place at the atomic level, no instrumentation was available in the world. So what we did was to decide to build it in our lab. Okay, just myself, Ed Boyce, and our technologists. So you can do it. And so I'm going to talk about design and developments of the novel in situ environmental microscopy for catalysis at the atomic level. So why are we interested in atoms? Atoms make up everything, right? And so let's take a look. We need to visualize and analyze atoms in action in real time during catalysis. And there are a couple of dimensions here for you to remind us. 1 nanometer is a billionth of a meter. 1 atom is 1/10 of a billionth of a meter. So they're invisible to the human eye, but they are fundamental to matter, and also they're fundamental to chemical reactions. So how difficult is it to look at moving atoms in a chemical reaction? It's like looking at moving golf balls on the surface of the moon from the planet Earth. Can you see them? So that's the sort of complexity that we are involved with. However, and therefore to address that, we developed the world's first atomic resolution environmental electron microscope. We developed as the key tool for dynamic reactions, and basically to unlock the changing atomic world and to develop improved catalysts and processes for human benefit. And as I mentioned, we need to understand the relationship between the synthesis, dynamic atomic structure, and properties. And in other words, we need the right tool for the job. For example, in gas-solid reactions, we need to have access to intermediate phases, which can be active. And also, we need to understand the chemical composition changes. So we need analytical atomic resolution reaction environmental transmission electron microscope. We simply call it atomic resolution ETEM. And so this is our, but there was a big problem, right? All the conventional electron microscope operates in high vacuum at room temperature, but our chemical reactions take place in gas and temperature environments. No instrumentation was available, so what was the solution? So we designed and constructed the atomic resolution ETEM for gas. Today I'm just going to concentrate on gas and temperature, not on liquid, in our research lab before electron microscope manufacturers and other institutions did that with lots of money. So we wanted to be the first, and we wanted to do it in our lab. And of course, there are risks in breakthrough technology developments, but we need to take risks to advance science. So many of you are familiar with this TEM electron microscope. You can see electrons incident on the sample. We have various signals here. A lot of them transmit through. We form a TEM image, and also X-rays come out. We can do chemical composition and also electron energy loss spectroscopy to get chemical composition. But the important thing in single atom is STEM, scanning TM, where a probe of electron is scanned across the sample, and we collect these high-angle scattered electrons called Rutherford electrons. And it was invented by Crew in the mid-70s, I think. And here, important thing is the intensity is approximately proportional to Z squared. Z is the atomic number. So if you have platinum on carbon, for example, platinum is going to look very bright. So conventionally, electron microscope, as you saw in the last couple of days, it operates in high vacuum at room temperature, and people have done fantastic work with atomic structure defects, electron diffraction, which follows Bragg law also. But we need to do all these under reaction conditions, so that's the challenge. So we developed the world's first atomic resolution ETEM under reaction environments. In developing the first ETEM, we took a different approach. And basically, we used the electron microscope sample chamber itself as the chemical reactor and radial pumping holes in the imaging lens and gas in the microscope design. We can put we have differentially pumped column zones separated by a series of open apertures, so we call it gas in the microscope design. And we can use controlled heating and various gas pressures, and basically gas flow horizontal and electron microscope vertical here. And we always do calibration experiments to minimize the beam damage. First of all, we do the experiment with very low beam currents, and then we do the same experiment without the electron beam and switch the beam on just to take the final reaction endpoint and compare the two to ensure that the beam damage is minimized. So with all that, we get fantastic data. As you can see, this is the first ETEM we built, and it looks like a chemical reactor. You can see gases going in, a hot stage here, and the schematic is the one I explained before. And for the first time, we saw clusters on graphite at 500 degrees C in nitrogen. So it was a eureka moment, We showed that atomic resolution was possible at gas and temperature environments. So it opened up a new areas of research in catalysis and materials. We did not patent it. We published the whole thing, so it's adopted for commercial production. And all these Techni and Titan ETEMs are replicas of our instrument. And in fact, it's used worldwide, and it exceeded our expectations, let me put it that way. And so it also inspired MEMS-based gas window cell holders, because they came and talked to us after we showed that atomic resolution was possible in gas and temperatures. So these MEMS-based gas window cell holders came along, and many people are using those as well. So it led to another technology also, and brought a lot of scientific and economic benefits, which are highlighted by Materials Research Society. And so we also developed various practical applications, coatings, nano coatings for pigments, for green paints for housing, vehicles, etc. And also in healthcare, for example, we have liquid medicine with solid coating. It's one of our inventions, and also hydrogen storage and so on. So a lot of practical applications also came along. But then, let me see. Yeah, and then we advanced with scanning. So in New York, we then decided to put ETEM and ESTEM in one instrument, and we advanced it with scanning and do single atom dynamics in high temperature, high pressure conditions. And for that, we established a nanocenter at York. And then we constructed the ETEM and ESTEM. We simply call it ESTEM. And we incorporated aberration correction, which I'm going to explain in a minute, of imaging lens. And then we accommodated regular holders, controlled gas environments, and gas in the microscope design. And so we can do dynamic single atom imaging with resolution down to 100 picometers. So it allows us to look at single atom dynamics. So in late 1980s, Max Heider in Germany came up with spherical aberration, whereby imaging lens aberrations are corrected. It's like putting glasses on the microscope. Without aberrations, you can see electrons don't focus. You have a particle here, but it's very difficult to see. But with aberration correction, you can see the particle very clearly, even the atom columns. So that's the aberration correction we use. And we also have gas and temperature in our ESTEM. And it allows us to visualize single atom dynamics in gas and temperature. So we can look at reacting single atoms in action. And so this is a little bit more complicated than our first ETEM. You can see ESTEM on top, ETEM at the bottom. And this is the same principle here. Gas electron sample chamber itself is a gas chamber, and we can do gases and heat. And again, reactor this way and electron microscope vertically, so we can do single atom dynamics. This is the final product. You can see it much more shiny, and you can see STEM and TM at the bottom. It's in the whole thing, so we can, just with the switch of a button, we can change from E-STEM to E-TEM. We call it York E-STEM, S-STEM. So it was the first one in the world to do single atom dynamics. So here, with all these changes, we have maintained single atom resolution. This is these dumbbells in silicon separated by about, this is not working, eh? 0.136 nanometers. Is it working? Okay, 0.136 nanometer. So these are the dumbbells in silicon. So we can maintain single atom resolution. So both these things actually came in the front cover of journals. This is the MRS bulletin, our E-TEM here, and this is our E-STEM in Annaländer Physik, which is one of the oldest journals on the planet. So again, I'm an experimentalist. I believe in seeing is believing for me, okay? So for example, if you take gold to the nanoscale, it becomes highly active, as many of you know. It's used as a catalyst. But theory predicted that nano gold particles are round, but they're never round. In the experiment, they're always faceted, and they have these tiny atomic scale defects. That's where catalysis happens. So please be careful. It's always important to confirm theory with experiments. And so I'm going to give a couple of examples. How are we doing? A couple of examples, platinum carbon of interest in fuel cells, and to meet energy demands and reduce environmental pollution. And then I'm going to talk a little bit about sustainable fuels. So as I mentioned, this we can, in our instrument, we can do E-TEM and E-STEM at the same time that we built. And E-STEM is very clear. You can see single atoms and clusters and nanoparticles very clearly. In E-TEM, it's a little bit more complicated because of diffraction contrast effects from the substrate. So we use E-STEM for single atom dynamics. So this is the same figure that our student Michaele has colorized. You can see single atoms very clearly, clusters and nanoparticles here. And basically, we can quantify these by using intensity profiles. You can see that's the atom A here. It's about 100 picometers. So quantification is important. And then we can look at single atom dynamics in hydrogen. This is the fuel cell catalyst. This is at room temperature. And you can see single atom here and a lot of single atoms with no gas. But as soon as you put gas in, they start to react. And then they move and reattach themselves to other larger particles, form clusters and so on. And the particles start to facet. And at higher temperatures, you have more faceting and also more clusters. So you can actually study the dynamics as a function of temperature and gas atmosphere. And here is an example of the single atom that we have caught, and you can see they move around quite rapidly, but we can actually stop that and take video stills. So we can actually catch them during the reaction. This is the video still from the same video, and you can see here that's the same particle. Same particle P here, and you can see 3 atoms come out. 4th atom comes out, and as soon as it finishes giving out all its atoms, it starts to facet. And once it facets, it doesn't have any more atoms to give, so it becomes redundant in the reaction. So it gives us insight into the mechanism at the single atom level. It's telling us that minimization of surface energy of the irregular particle is the driving force to remove these single atoms from the surface, and once all of them are gone, it becomes faceted. So it gives us insight into the nanoparticle development and tells us that once the nanoparticle is faceted, it's no good for catalysis. So it tells us what sort of particles to use in catalysis, how to stabilize these atoms, and so on. So tremendous insights which we did not have before. And also, in supported nanoparticle catalysts, particle growth can occur, and we call it sintering. So once it sinters, obviously surface area is reduced, and it becomes the catalyst starts to deactivate or degrade, and it has potentially devastating economic consequences. So literature reports, before we built this instrument, people around the world had no idea how they sinter. So they came up with the idea of particle size distributions. If the particle grew, they said, okay, some particles must have joined it, but they had no way of knowing how it grew. And so for the first time, we can get single atom level information into the sintering process. And here is an example of how this video should work, actually. Here you can see how the small particles actually move and become large particles. So you can see it loses surface area, atoms also move around. So it's very important to know when this happens and at what temperature it happens, so we can take appropriate measures to change the temperature or also change the composition of the particle or composition of the gas. So it's very important information we can get from the videos. And in the literature, the two methods are suggested. One is the Oswald ripening, where movement of small atoms from small particles to large particles take place, and then resulting in the larger particle growth. And the other one is a particle migration, where it involves the mobility and coalescence of particles. And so for the first time, we can study these at the single atom level. So this is a nice image. As I mentioned, it's like looking at moving golf balls on the surface of the moon. Our student, Thomas Martin, has done a fantastic work here. You can see he's actually captured them whilst they're reacting. Let's focus on the particles 17 and 18 here. After 40 minutes, they have decayed a little bit, they have disordered, and more single atoms coming out, so single atom density changes. And also after 70 minutes, they've completely gone. They've decayed and more single atoms here, single atom density increases with the loss of particles 17 and 18. And they then start to move and join the larger particles, and the larger particles actually grow, as you can see here, so sinter. And so we can quantify that. This is the particle 17 comes down and decays, and particle 18 comes down and decays, and the single atom density actually increases. So it tells us a great deal about sintering process. Tells us that single atom density increases as the particles decay, and they then start to reattach themselves, and resulting in the growth of larger nanoparticles. So stabilization of the single atoms is important in catalytic process. And so the other example I'm going to talk about is the transportation fuels that we all use. And this is an industrial process. It's one of the major processes to produce transportation fuels. It's a sustainable process. It's basically we convert syngas, which is the hydrogen and carbon monoxide, into, and then we apply what's known as the Fischer-Tropsch process or FT process or cobalt-based catalyst on silica and other oxides. And we basically make syngas from biomass and waste, so it is a sustainable process. And and most transportation fuels in the world are using this process. So it's important to optimize the FT process. And we work with Johnson Matthey on this one and published a couple of detailed papers. Basically, half of these are from Johnson Matthey. And it was led by our postdoc, Robert Mitchell. So I'm going to talk about how we did it. We basically developed 3 treatment methods. One is drying and calcining, which is called DC, at high temperature and high time scales. And one is the drying reduction, which is D, which is the low temperature and low pressure. So I'm going to talk about DC and D here. And we then activate in situ in the E-stem in hydrogen at 400 degrees centigrade and correlate the data with chemical experiments like ESCAR, drifts, and then catalytic activity measurements, which I don't have time to go into, so to obtain basically deeper insights into dispersion and activity of the catalyst. So we can do all our chemical composition, dynamic electron diffraction, imaging at atomic scale, all in one instrument, so you don't have to take it around. So DC, for example, done at higher temperature shows larger particles, but and distribution of cobalt, silicon, and oxygen. But here, D actually shows finer particles and uniform distribution of cobalt, silicon, and oxygen. And it gives us tremendous information. So we can do dynamic electron diffraction, which follows Bragg's law, to look at various phases present in the catalyst, FCC or HCP, and so on. And then we can do single atom dynamics. They can track the atom movement as a function of time at 400 degrees C. This is done at a few minutes intervals, so you can see lots of atoms. This was a revelation. Nobody knew they had so many atoms and clusters, and it reveals a lot of atoms and clusters. And we can also quantify the single atoms using the intensity profile. And then we can correlate that with catalytic reactivity measurements. I'm going to talk about the first two on the silicon silica support here. And you can see C5 plus hydrocarbons, that's our fuel. And you can see tremendously highly active catalyst, because it's given us almost 90% of the selectivity, which is very good. For industry, 50 to 60% is good enough. So these are extremely powerful catalysts, and our pre-treatment method has worked, and these are various C2, C4 chemicals. So in D, we see that a large number of low coordination metal atoms and clusters, they indicate basically higher number of active sites for absorption of the reactants of hydrogen and carbon monoxide. And these in situ ETEM data generate atomic structural insights into catalyst dynamics, which are important in the development of these catalysts for transportation fuels. And in summary, we have developed the first in situ atomic resolution ETEM and ESTEM to study dynamics of chemical processes under controlled reaction environments, which are leading to new opportunities all over the world, and they are highly productive, and insight into the role of practical nanoparticle catalyst and catalysis, catalytic fuels as well, and technological economic benefits, quite a lot of practical applications as well. And they've also inspired gas and liquid window cell holder technologies, and they may also facilitate development of new catalyst and clean processes. So basically our ETEM is used globally for commercial production and by chemical companies as well as by researchers. And advances in ETEM and ESTEM are deepening our understanding and how these catalysts work. And as eminent scientists said, new instrumentation lead to new science. And that's absolutely true in our case. Without our development, we could not have seen any of these. And we believe in science for society. And these are various people who contributed the work. And boys here, Ian Wright, our technologist, who is extremely good, and all our students and technology postdocs. And this is Michaele here. And they all have poster sessions to discuss their ideas. And I thank you for your attention.
So are there any questions for Pratibha? One at the back.
Yeah, thanks for that presentation, and congratulations. It's such a major development in electron microscopy. It's been so important. I'm glad you put up the bullet about gas and liquid cells. So what is your opinion, or what do you think the future is? With the development of silicon nitride membranes and graphene membranes, is the future of environmental electron microscopy now in the holders and cells rather than in differential pumping and using the environmental TEMs?
Okay, many ETEMs that have been sold worldwide are differential pump systems based on ours.
Right.
And I mean, I don't know, dozens have been sold. But with the holder, there are limitations. They're still evolving in terms of resolution and chemical composition analysis because of the thick silicon nitride windows. There's several nanometers on top and several nanometers on the bottom. So it's very difficult to see single atom dynamics very easily. And also, chemical composition analysis is difficult because of the windows. They obstruct X-rays and things like that. So obviously, they are much easier to do for many people. Just buy from commercial vendors. These are actually, we have developed them in-house. But you can do that. I mean, we have published all the details, and some people have done that as well. So it depends on what your aims are. But I would say both have future. And but as I said, holders are still evolving, and they're not very easy to get single atom dynamics very easily at the moment.
Okay, thanks.
And in the graphene, there is a problem of enclosing gas or liquids, excuse me, and the graphene windows may break during the reaction. So that's happened to many people. Excuse me.
Any more questions?
In any systems, is it clear whether it's single atoms or small, few atom clusters that are the most active species?
Please repeat that.
I mean, your data over the years has shown a lot of evidence for single atoms and very small atom clusters. In any particular system, is there evidence which are the most active species for the catalytic reaction?
In our systems, we work with technological catalysts. We have both single atoms and clusters. I think both are important for different applications, for different absorption.
Okay.
At the moment, we don't know which one is better, but I think single atoms may be better. But what happens is it's very difficult to stabilize them on an industrial support because there are cracks and things. They always move and form clusters. So we don't know really, after the final result, we don't know how it happened, whether the single atoms were important to clusters. We get the combination.
Thank you.
Okay, if there are no further questions, I think in the interest of time, we need to move on. So let's just thank Pratibha again.
Thank you. Very much.
So next this morning, we have my colleague and friend from the School of Chemistry, Professor Michaele Hardie. So her expertise lies in supramolecular chemistry. So she's really constructing functional materials from the molecular point of view. So Michaele comes from Melbourne originally, moved to Leeds in 2001, I believe. And she won the Morgan Prize from the RSC in 2011 for her research in this area. So today she's going to talk to us about her research on the assembly, structure and function of coordination polymer and MOFs.
She will if she can figure out which direction to go. Ah, got you. Okay. Thank you very much for the introduction, and thank you so much for the invitation to come and speak to you today about something a little different from what we've heard thus far this morning. So this is going to be very chemistry heavy. So first of all, just to acknowledge the people who did the work. So the main players in this presentation are Tia Jacobs, Haida, Matthew, and Flora. And just a very one-slide overview of the sorts of chemistry that we do in my group is that we are, as Fiona said, supramolecular chemists. We spend a lot of time in designing and synthesizing new molecular host molecules, such as these. We use those either to link them together to form small cage-like structures to bind other molecules. This, for example, is a molecule or a cage that binds methane in solution. Or we use them as components to self-assemble much more complicated structures using metal ligand ion assembly. So this could be cages again. So here is an example of a palladium-linked cage which binds iodine in the solid state. Or this is an example where we're using iridium so that we've got luminescent cages. These ligands tend to be chiral, so they can show some quite interesting self-sorting of the chiral ligands in solution phenomena. And we can also embed some functionalities such as structural photo switching within the cages. But they can also be used to form MOF, or metal organic framework, or coordination polymer type materials where we have extended structures. Just a couple of examples of those, as well as other types of extended network crystalline materials. But we also do some MOF work using much simpler ligands today as well. And so today I'm just going to focus on this area here, the use of these tripodal ligands, but also really simple ligands to build complicated molecular metal organic framework type materials. Okay. So if we take tripodal molecular host ligands, introduce them to the metals, grow some coordination polymers, there is absolutely and utterly no predictability whatsoever in the types of structures that they will form, only that they tend to be quite complicated. And one of the nice little subsets of structures that you can see is where you have cages within your networks that can then get linked through the metal centers to form larger assemblies. And this is just some examples from our own group and also from the literature as well. And some of these can have some quite nice properties. So for example, looking at this one here with this ligand, and this is an example with copper, when we've got the small cages linking to, each small cage links to 3 others to form a hexagonal network, which then within the crystal forms AB stacking patterns, leaving these really huge gaps within the crystal lattice, as well as the small confined pore space of the actual cage. And this is the material here, these little blue crystals, and they're very delicate. So if you so much as breathe on them funny, they completely fall apart. But if you keep them under their mother liquor, then they're perfectly stable, and they can be used as, say, a heterogeneous host for binding fullerenes such as C60. So we can see that C60 goes into the crystals if you just simply soak them in a solution of the material. This example here, where we have each cage structure actually linked to 6 other cage structures using rhenium, again gives you a material that can act as a heterogeneous host. It can bind other molecules from solution, in this case iodine. But this is a much more stable material. It's quite robust. You can pull all the solvent out, it's perfectly happy. And we've also just, in some preliminary work of seeing that it can be used as a heterogeneous photocatalyst for doing things like photodegradation of dye materials. So methylene blue, for example, in about an hour, you see about a 40% degradation of it. But something with no obvious application that I can see that's a little bit fun that we can see with these sorts of materials is with this ligand here with copper in DMSO, and if we've got the bromide, and this is very, very specific to these conditions, we can form a material, or a metallocycle, we call this, where we've got 6 metals, 6 ligands, all linked together in just this big cyclic array. And there's actually 2 of them within the material, one of which, where at each of these coppers we have bromides, and in the other one at every single copper, we've got bromides at every single copper, but in the other one, sometimes we've got bromide, sometimes we've got water. And these grow in unusual crystals that are needle-like but completely hollow. We've got loads and loads of SEM images of these, that they're always growing in this manner, so they're completely hollow. And if there's any other single crystal crystallographers out there, it's really difficult to get a decent structure from a hollow crystal, but we did eventually do so. And we've got this metallocycle, and we were not particularly excited. We thought this isn't a very interesting looking material. Let's just get some solution chemistry and send it in as a quick communication. But we couldn't dissolve it. And we didn't understand why we couldn't dissolve it until we looked a little bit more at the structure. And if you look a little bit more at the crystal structure, and if you look at, instead of just 1 ring, we look at 3 rings next to one another, and I'm highlighting here a DMSO molecule which is coordinated to a copper, and that's where these rings get closest to one another. If we look at 3 rings in a row, then they're entangled with one another, but not in the way that you might think. So it's not forming a chain structure, so we're not linking like this. What we see instead is something termed a Borromean ring assembly, where we've got, say, purple is going over green but under grey, grey is going over purple but under green, etc., etc. And this is a type of topological arrangement of 3 rings that can't be pulled apart unless you break one of the rings, even though you have no specific chain interactions, no sort of threading through of the rings. And if we look a bit more at the structure, then every single metallocycle is surrounded by 6 others, and if we explode the view a bit, then at each of these points, we've got 6 different Borromean ring associations. Extend this out to the whole structure, and we see a 2-dimensional layer just of Borromean rings. So it's kind of a chainmail of Borromean rings, which had never been seen before, and I'm not sure there are any other examples that have come out recently as well. Now you look at this and think maybe this is going to be a really interesting 2-dimensional material, but we've got to remember that it's actually ionic. So there are going to be some counter ions around, and in the full crystal structure, that's the bromides, and they sit between the layers, but also into the lattice structures. Okay. So what about simpler ligands? These things are ligands I've just been showing will take a week or 2 to make in the laboratory. They're not something that's ever going to be easy to scale up. What about materials that you can either just get off the shelf or make very, very easily? So looking at some MOF materials from taking a combination of a carboxylic acid donor So with these, the carboxylic acid, if you pull the hydrogen off, you get a carboxylate, such as here, which can bind to metals. And combine that with a linear N-donor linker, where these pyridyl groups can also bind to the metals. And I have to say at the onset here that there are many, 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 many groups out there that do exactly this. Take carboxylate and N-donor ligands and combine them to make MOF materials. And in the vast majority of cases, what happens, what sort of structures you get, is what's termed the 3D pillared layer structures, sometimes also called the jungle gym structures, where you get a square grid array of your metal and the carboxylate. Sometimes it's a single metal, sometimes it's a dimer. So this is a typical paddle wheel dimer, so 2 cobalts there, bridged to give you a square grid type structure, or SQL if you want to use its standard nomenclature. And then these are then linked together through these long N-donor ligands to form this pillared array, or the jungle gym type structure. And in most cases, or in many cases, what happens is instead of seeing just a single framework like this, you get 2 of them interpenetrating. So 2 completely independent networks that are chemically absolutely identical, and they intertwine with one another. And these are of interest because they will bind other molecules, and when they do that, they tend to show really quite complicated structural behavior. So when you pull solvent out, they go undergo structural changes. When you put other things in, such as carbon dioxide, methane, hydrogen, such as, etc., you also see a lot of structural changes. And indeed, that happens with this particular system, but that's not what I'm going to talk about today. We don't have time. It's really, really complicated. So instead, I'm going to look at a related material with a very small adjustment to what our chemical starting material is, which is just to use a slightly longer carboxylic acid. And when we do that, we get the paddle wheel of our cobalts, we get our carboxylic acids coming off, but instead of forming a square grid structure, they form a 3-dimensional structure if we're just looking at the metals and the carboxylates. So this is the same, topologically, it's the same structure as cadmium sulfide. And these link together through these N-donor ligands, and there's actually some quite complicated interpenetration of square grid networks there, which are then linked together through these to form a single network, which is itself entangled. So it's a self-interpenetrating network. So it entangles itself, but there's only one network there. And this is a very robust material. We can pull out the solvent that you form it from. You can look at the gas absorption properties. So it is a reasonable binder, for example, for hydrogen, but it's not a spectacular binder for hydrogen. There are much better materials out there. What it is quite good at doing is binding ethanol. So if you take the desolvated crystals and put them into a jar of ethanol, you can see the air being displaced in real time, so it sucks up ethanol very, very quickly. It will also absorb ethanol in the vapor phase and is particularly good at doing that. And what we see is that it's robust enough that at every point it's the single crystals, so we can look at the structures and when we make it, when we desolvate it, and when we put ethanol into it, and we see virtually no changes at all. So a very robust material. It's not robust to water, however. If you put it into water, it will decompose. So this is typical for MOFs. The metal to carboxylate bond tends to be hydrolyzed, but it does so really quite slowly, and it does it slowly enough that partway through the process we can pick out a single crystal and put it on a synchrotron and get an intermediate species when it's partway through decomposing. And what we find that happens is as it decomposes, it releases its ligand into solution, and then it binds its own ligand into the channels. So this is essentially the MOF that ate itself. Another example just of how complicated these structures can get from really, really simple starting materials is this one here. This is very similar ligand, except we've got a less flexible linker group, and our pyridyls move to the 3 instead of the 4 position. and this is with nickel. And this gives crystals which are in a chiral space group, despite coming from achiral ingredients as such, where we've got, again, carboxylates, and we've got binding end donors. If we just think about or look at what the carboxylates do, we've got this two nickel clusters linked together by the carboxylate ligands into a diamond-like framework. So this is the same basic structure as diamond, whereas the end donor ligands are forming these grids, and throughout the lattice there's lots of them, and again there's interpenetration, in this case in an orthogonal manner, so 2D to 3D interpenetration. And the full structure is all of these put together, again forming just a single network, which shows incredibly complicated interweaving throughout the material itself. Okay. And these have quite a lot of potentially accessible void space. Unfortunately, we've not managed to grow them in many more than one crystal at a time, so we can't tell you too much about the properties on this one just yet. And just one more example to finish, where our ligand this time is a little more complicated than earlier. So we've still got the two pyridyl groups that combined to metals, but in the middle of the ligand, we now also have potential metal binding groups. And combining this with zinc and this time a bent dicarboxylate ligand, we get a material which again is going to be in a chiral space group. And that chirality comes from this helical chain of zincs and carboxylates, which runs through the structure. We can see that the zinc is tetrahedral, two of these pyridyl-type ligands coming off at this end. We're now going to look at one of these chains from above. So that's this one here, and it's got some adjacent chains next to it, and then these pyridyl groups are going to bind to another cluster like this elsewhere in the structure. So this is what we're looking at before. It binds to another structure kind of over here, which comes around, and we form loop-type structures through this way. So again, we're seeing a single interpenetrating network with really quite complicated topology and a very, very robust material. So we can pull all the solvent out, and it has a moderate surface area. But what we do have here is a metal binding site with no metal in it. And when we look in detail at what's going on around that metal binding site, is that we've actually got two of them set up, seemingly ready to bind the metal. So this is our as synthesized crystals. We can just looking at our ligand binding to a zinc here and a zinc here. Here's our quite disordered bipyridine, but there's another one here, and these distances here look absolutely perfect for being able to put in other metals. So if we start with a homonuclear material, we're going to add another metal, so in this case copper, and we can see a color change, and these remain as single crystals, and we can then see that the copper has gone into that position. So it's infusing through the network structure and picking up copper-type materials. Interestingly, when we look at the nature of that copper, so looking at EPR and EDX, so seeing how much the copper to chloride ratio is, for example, it looks like even though we put in copper 2, it's copper 1 is the species that's going into that position. Probably DMF is doing some of our redox chemistry for us there. Okay, so that's all I wanted to talk about today, just to highlight all the people who have been involved with this work. So anyone who's been involved is highlighted in pink. That includes postdocs, PhD students, as well as some MChem and MSc students, as well as some collaborators, both within Leeds and outside of Leeds. Funding agency, I need to give a particular nod to the Iraqi Ministry for funding Hardie's research, and also some reasons here of why I like to live in Yorkshire. So thank you very much.
Thanks.
Thank you. This might be a bit of a silly question. What would be the practical application of a polymer that absorbs alcohol? I'm assuming it's not to take alcohol out of breath for breath analysis. Could it make it easier in terms of taste, removing alcohol from wine?
Oh, that's an interesting suggestion. I'm not sure I would actually want to use this material for removing alcohol out of wine because cobalt tends to be pretty toxic.
That's why I asked practical applications.
Yeah, so this one in particular I wouldn't necessarily go for, and of course we also see it decomposes a bit when the water's around, but I think when you're looking at absorbance, really the next thing to do is look at a competition and see if it could remove ethanol from something else. That's where potential applications actually might really come in. And ethanol is the first one we tried, essentially. It may well also bind other things. So because we've got NH groups on the ligands, we're looking at polar guest molecules that can go in. So there's other sorts of separations of different sort of polar. But yeah, I wouldn't be drinking wine after the cobalt's been soaking in cobalt, I'm afraid to say.
Thank you.
Hi, Michaele. Sorry if this is a really stupid question, but when you dissolve in your second metals, have you got any idea what the occupancy level of those sites are?
I should have, but I can't remember because that was quite an old study. But it doesn't completely go in, but it's a reasonably high percentage.
Thank you for a wonderful talk. Really enjoyed that. A general question. So MOFs and COFs and cage compounds have been touted for, 15, 20 years as the sort of answer to everything. And I know there's one application of a MOF in carbon capture, but realistically, what's your opinion of, the industrial use of these materials?
Realistically, what's my opinion of the industrial use? I think of the early work I showed, realistically none, because unless it's a really niche application, because they're just too expensive and too long to make. But these sort of things are easy to make, and you can make them in bulk, and many of the MOFs that people look at are easy to make and can be made in bulk. And then I think the problem in the MOF area is that it promised, or certain people within the area promised, that they would change the world in terms of things like hydrogen binding. And I don't think that's ever actually going to happen. What do you reckon? I don't think we're going to get there on hydrogen absorption. No, not. But there are other things. So there's a carbon capture. I think there's some really interesting work going on with proton conduction, for example. There's some nice work with catalysis. Everyone is moving more towards catalysis. I think that may be an admission that maybe the gas binding's not going to be what they thought it was. But also there's some interesting work, I think, with delivery of drug agents and things, not with cobalt ones, but with some of the more benign metals.
Great, thank you.
Fiona.
Thank you for your talk. Sorry, again, maybe a naive question. Sorry if I missed the pore sizes you form with these MOFs. But the non-centrosymmetric space groups, you've got the chiral ones. Could you use them as kind of chiral sieves for separation of molecules? And has that been done? Because that's quite...
It's not by us, but it's certainly other people have looked at such things. So the size of those pores, I'm not going to be able to give you the exact size, but they're not tiny, so they would be in the sort of nanometer size. I think the biggest ones I maybe showed was about 10 nanometers across, so typically big enough for individual molecules, which is kind of what you want for separations. I think early in the MOF days, bigger was thought as better, but actually it's not. What you want is smaller and functionalized. So yes, conceivably, you could look at these for chiral separations. Although there is the problem, of course, that I would have to check if we're getting both, have a look at a sample to see if you're getting a conglomerate or if you're getting or not. Yeah.
Great, thank you very much. So I think we need to move on.
Yes.
So our final speaker for this morning is Dr. Matt Hughes, who is a research fellow in hierarchical biomaterials in the School of Physics and Astronomy. So Matt completed his PhD here at Leeds in 2021 on the translation of protein stability across different length scales, for which he won the Radford Jordan Award for the best PhD thesis in the Asprey Centre. So his work now focuses on capturing the dynamic formation and self-assembly of protein networks, which he's going to tell us about today.
Awesome, thank you very much. So I'm Matt, and I'm going to give you a whistle-stop tour of capturing dynamic assembly of protein networks. So understanding how protein networks assemble is really important. So an example that I think Tamir covered in a really excellent talk yesterday was fibrinogen networks or blood clots. So them forming correctly in the correct place, in the correct time, in the correct way is really important so that you don't bleed out, or that if it does it wrong, you'll lead to embolism. So it's very important on a kind of fundamental biological way. It's also really important to understand for predicting the properties of materials. So another sort of big bit of work is understanding how particles in suspensions will build networks, for example, proteins in suspension, how they build networks, and how this could be used to develop biomaterials with predictable properties. You can't, as we've seen with a lot of the materials that have been presented here at the Bragg Exchange, predicting the properties is really important for any application we want to use them for. So the question that I hope to be able to answer in this sort of brief talk is, what are the key formation mechanisms that we see in protein networks? So to do this, we need a model system. So I'm going to use photochemically cross-linked folded protein hydrogels, which is a long name. But essentially what it is you take some protein in solution. This one we use here is bovine serum albumin. This is our model protein. So serum and albumins are a blood protein. This one just happens to be from a cow. And it's got this kind of folded structure, which realistically is just a blob, is the way I'm going to think of it from now. So it's going to look like this sphere. You take a bunch of those, you apply some reagents and some light, and they'll start to cross-link together. And you keep doing this until you get a mature gel at the end. And the reason photoactivation is really important is it gives us a lot of control. So I know exactly when I'm starting gelation. It's not a matter of adding chemical, waiting for it to diffuse. I can turn a lamp on, I can turn a light on, and know that it's starting at that point. So the technique that we're going to use to investigate this, or I'm going to talk about the most, is I think really sort of important to the Bragg Centre, is X-ray scattering. I'd love to say that I thought of this connection much earlier, but I thought of it about 10 minutes ago, which is quite sad, but there we are. But we're going to, in particular, we're going to do time-resolved small angle scattering. So what you do for that technique is you take your sample, you fire some X-rays at it, the X-rays scatter off, and then you capture a frame. You can sort of think of this like taking a photo at this point in time. It's a little bit not like taking a photo. I'll cover why in a second. But essentially, we do that, and then we turn the lamp on, and then we capture another frame, and another one, and so on. So it's a bit like, in the same way, it's a bit like video. You're just stacking photos against each other. It's not like video because it takes ages. And then you can see here that you've got this sort of pattern here where you've got a big bright spot in the middle and then a kind of halo around it, right? That bright spot in the middle is the beam, and the halo around it is all the scattered X-rays. So that halo of scatter is what tells us all about what our system looks like. It's very hard to analyze that there, so we do a 1D reduction, and I think you'll agree this is much easier to look at, right? What we can do here, so this is a really ideal technique to study how systems evolve over time, because an important note is you can do this completely in a native environment. So that's in water, the sample's not frozen, it's not put in different kind of solvent, it's in its sort of native solvent in a native way. So one of the first tips we get is an example of one of the scattering curves we get at t equals 0. So this is what protein looks like in solution. And I imagine a lot of you are looking at me going, Matt, that's not what a protein looks like, and I sort of agree with you. But the key thing we're doing here is that you can't, why this is not like a photo is you can't lens X-rays back. So when you take a photo, it lenses it back into a picture. Can't do that with X-rays. So you get these curves that like this that have been sort of Fourier transformed from real space. So what we're in here is Q space. And the way you can think of that is it's inverse space. So little q means big thing, and big Q means small thing. For those of you who are really big in CM, it's a bit like 2 theta as well. That's an easy way to think about it. So what we do is we take multiple of these curves over time. So I've done these in 2-minute intervals, and then you keep going for another 2 hours, but I'm not going to show you all that. And what you can see here, there are 2 sort of key regions. You can see there's this power law region here, so it's kind of this, in this middle bit here, there's this power law. And then there's this turn to plateau. Oh, I've got a laser pointer. There's this turn to plateau here where it starts to plateau. And those 2 sort of key bits of information we get from that. From this power law region, we get an idea of shape geometry, kind of what the object looks like. And then this turn to plateau tells us about how large that object is. So over time, what we're seeing is that this plateau is moving to the left, this turn to plateau is moving to the left, which means the object is getting bigger, which you might expect as it starts linking together. And you can also see there's a change in the power law here, where what's happening there is it's suggesting there's a change in the morphology, that something's changing about the geometry of the system. So we can definitely follow this using time-resolved SACs, but it's all a bit qualitative, so to get a bit of quantify a little bit, we can use scattering models. So previously we've shown for mature gels, we have this fractal-like clusters connected together to form the mature network. And we can use that to analyze out and get two key pieces of information out. The first one being the characteristic length scale, the fractal clusters, basically related to its size, to how big it is, and you can see that grows over time. Again, this sort of intuitively makes sense. If they're cross-linking together, they're going to get bigger over time to a certain point. And the other one is the fractal dimension of those clusters. So the fractal dimension is quite a complex parameter, but the way you can think of it is how complex the cluster is, how complex is it put together. Or another more intuitive way of imagining it is how densely packed is that cluster, how many proteins have been fit into this sphere that we're going to call a cluster. So what we can see here is time-resolved SACs combined with scattering models lets us track really specific parameters that can give us an idea of how the network is evolving over time and might give us some insight into its formation mechanisms. We can combine this with rheology. So unfortunately, I haven't had time to talk about rheology in this talk. Please ask me about it at lunch. I do like talking about it, so please. This bit here on the right, this G prime, can be thought it's the storage modulus, or basically the rigidity of the network. And what you can see is the rigidity network with these solid symbols, flat for a bit, jumps up in strength, and then starts to plateau at the top. And we can combine this with the scattering, and some simulation work. We can see here that we get one bit here where there's a big drop in the fractal dimension and a sharp increase in the rigidity. We've called this the primary formation, so this comes from the diffusion of single monomers in solution, which are then cross-linking together to form this preliminary network, the first sort of self-supporting network. It additionally also forms these sort of smaller oligomers, which are not yet part of the network. So we'll come back to those in a sec. We then have this second phase where you see that you're getting this increase in the fractal dimension with time rather than a decrease. So what this is suggesting is the network is getting denser. It's densifying over time. And you're slowing down how quickly the mechanics is increasing. And what we think is happening here is that these oligomers, which are more slowly diffusing the monomers, are cross-linking into the system. Additionally, the network is cross-linking to itself. So it's bending on itself to form new cross-links with itself, which is also energy punishing, so it's a lot slower. So I'll just skip this. Combining the the three techniques of rheology, simulations, and the SACs I've shown you, we're able to say that we've got a two-modal formation mechanism. We have a primary formation dominated mostly by the diffusion of monomers, and a secondary formation dominated by the formation of cross-linked oligomers and intra-network cross-links. So why does anything that I've told you about matter? Well, it's really important in a number of ways. Some of the bits I mentioned at the beginning in sort of living systems. So this is another example in amyloid fibrils. So the formation and propagation of amyloid fibrils is really important to diseases such as Alzheimer's. So understanding how protein networks want to form, both beneficial ones like fibrinogen and negative ones like amyloid, can help us sort of look to new treatments or new ways of attacking or dealing with disease. Other bits I'd say, like the development of biomaterials. So this here is a peptide hydrogel. And they're trying here to understand how it forms, because understanding formation and understanding how mechanics links to the network structure and how we can form that is really, really important for us to develop, as I said, these predictable biomaterials that we can use for sort of modern problems. And with that, I'd like to thank everybody here for all their help and support with the work, these guys for their cash, and everybody here in the Dugan Group for all their help and support. And thank you all for listening.
Right, we maybe have time for just a couple of quick questions. Anybody? Joe, well.
Thought I'd gotten away with them.
Hi, Matt. Great job. I just wanted to ask, obviously, you've used BSA as your model protein building block. Do you foresee any limitations on using your techniques to maybe follow smaller or larger building blocks in the same ways?
So you do have a limit on size, which is just, I'll go back a bit. your main limit on size will be, right, essentially what lowest Q can you reach will be the limit on your size. You can get to quite high Q and do reasonably smaller particles, so we have done smaller proteins than BSA. Large ones, so you, for example, large ones, if you were to study, I don't know, what's a really big protein? A ribosome, for example, would be a very, very hard one because it's massive. So you would kind of hit the edge. But the idea of if you can understand this model system, you would hope larger systems would follow. And we have seen in sort of large colloidal systems of microns, they follow a similar two-modal formation mechanism. So we just say, if we can see it on this level, then we can hopefully see hallmarks in the Q range that we do get. That makes sense.
Right, so if there are no further questions, I think we are going to close the session for today. And thank you to all the speakers this morning and to the session that I've just chaired.
Okay. It's now time to head over to the refectory for our final poster session. Please, if you haven't voted yet, please make sure you do so by the end of this lunch session so that we can award some prizes in the afternoon. And the next talk session then starts at 1 o'clock back here. Please do join us again. Thank you.
Well, welcome back and good afternoon. So my name is Christoph Wolti. I'm the theme lead for Bionanotechnology in the Bragg Centre, and I have got the privilege to chair the last session of this Bragg Exchange. So we have got 3 talks, as we had in all the sessions, and it's my pleasure to introduce Marianne Ashford from AstraZeneca. Marianne has done her PhD at the University of Manchester in oral drug delivery systems, has at some point later on in her career joined AstraZeneca, and is working on sort of nanomedicines, or maybe it's slightly differently put, still on drug delivery systems for all kinds of applications. So she holds, well, I was also supposed to say that she holds visiting chairs in Manchester and Nottingham, so she is very involved in the academic community still today. Thank you very much.
Good afternoon, everybody, and thank you very much to Andy for the introduction, and thanks very much to Chris for the personal introduction, for the invitation and the introduction. And thank you for all coming back after lunch and the poster session. So I'm going to talk to you this afternoon in this session on nanobiotechnology, on nanomedicines enabling the next generation of drugs. So I'm going to try and give you a very quick, to try and position it, a very basic introduction. Then I'm going to talk about 2 very different nanomedicines, a targeted dendrimer and lipid nanoparticles that I'm sure many people will have heard of post-COVID. So just looking and reflecting on drugs and delivery systems in the body. So here we've got the delivery, and here we've got the therapeutic modality. So for many years, we just had small molecule drugs, and then in the 80s, the antibodies came along, and then there are a few peptides for extracellular targets. And we tended to either give them orally, or we gave them parenterally, and they went throughout the body. The drugs distributed everywhere throughout the body. We're now moving, particularly with the antibody-drug conjugates and some nanoparticles and ligand-targeted systems, to more targeted delivery to get more of the drug where we want it, to reduce the side effects, which is extremely important, and is a lot more sustainable because we should be able to give less drug as well. And where we're going and where we need to get better at is targeted intracellular delivery, because that will allow us to deliver mRNA, siRNA, gene therapies. So it'll allow us to get to drug space that we can't get to and treat the diseases we can't currently treat with the small molecule and antibody modalities that we've got today. So I'm a drug delivery scientist, and I think it's a really exciting time to be in drug delivery. Typically, and I've put up here sort of a timeline from target selection and identification to candidate drug nomination to various phases of clinical trials and commercialization. Typically, we were given a candidate drug and we had to fix it as drug delivery scientists. We had a lot of poorly soluble molecules coming through and we fixed it here. And we were very much perhaps in the passenger seat sorting everything out. Now we need to get really back at target selection and the design of the molecules to make sure that we have the right modality, and it's making sure that we've got the active drug modality and the delivery system at the same time. So we're really going to be driving the next therapeutic, the next generation of therapeutics. And there's just a range of advanced drug delivery platforms that we're working on, and I'm going to talk about our targeted dendrimers and LNPs today. So targeted delivery is so important because lack of therapeutic index is one of the main reasons we don't get a lot of the drugs that we work on early to patients. Getting that safety, efficacy balance is a problem for at least 80% of the medicines that are worked on in discovery. And targeting delivery will improve that therapeutic index, it will reduce the cost of goods, and it will allow us to deliver those new modalities and genetic therapies. But what we've got to make sure is that we can get to the key organ or the area that we want to deliver to. So Paul Ehrlich first talked about targeted delivery in the late 1800s. And he talked about the magic bullet, and specifically to target and attack pathogens or disease cells without harming healthy cells. So it's been a concept for ages. And various people have tried to claim they've solved it. He started off with the nitrogen mustard for rapidly dissolving cells, and then we had the antibodies, more specific and molecularly targeted small molecules, and then nanoparticles, and then antibody drug conjugates, which is a nanocarrier carrying the drug, and then radioimmunoconjugates. There's a lot of progress, but we're not there yet. To really get to that magic bullet, I think we need several layers of targeting. We need to make sure that we've got some degree of tissue tropism, so that could be taking advantage of a disease state, it could be delivering locally. Ideally, if we've got a molecular targeted drug, it's better than a cytotoxic because there's some degree of targeting in the design of the molecule. If we can get site-specific release at the site, that's important. And perhaps if we use some concepts of multivalency and mimic some things that go on with nature, we can get more precision in our targeted delivery. Many of the targeted systems we've got at the moment are drug conjugates. And this was just taken from a drug landscape report earlier this year, and what is in a number of pipelines. And you can see a lot of the drug conjugates, 62% are antibody drug conjugates, followed by the oligonucleotide drug conjugates, where we can really deliver oligonucleotides very well with a GalNAc ligand to the liver. And then we've got our radioimmunoconjugates coming at about nucleotide conjugates, which are becoming increasingly an important modality, carrying targeted radiation, particularly in oncology patients. So a little bit about the antibody drug conjugates. As I've said, they're nicely shown up here. They're like a long circulating nanocarrier with a drug, normally 2 to 8 drug molecules, chemically linked to the antibody. There are 13, I don't think that's gone up in the last few weeks. I'd have to keep checking that they're moving fast. Having spent about 40 years not going very fast, moving fast with 13 approved products, over 200 in clinical trials. So there's a lot of activity. And a couple of relatively recent high-profile papers really recognizing perhaps that they are coming of age and perhaps the hype that was, we're beginning to see some reality. And then if you just see a rather nice trace here, this is a progression-free survival in breast cancer patients, 2 antibody drug conjugates, and after 12 months, 80% of the patients have survived, versus 30% with the early addition of an antibody-drug conjugate. So that's just really showing that with careful design and really understanding carrying more drug molecules and having a drug that can diffuse through the tumours, the benefits to patients of a well-designed antibody-drug conjugate. That's with the antibody Herceptin, and a colleague of mine said that very few antibodies behave as well as Herceptin. And the challenges of ADCs, that we are limited to the antibodies that we can use. You need to have a receptor overexpressed on target cells. There are very, very few. There are only about 5 payloads that are used, and we're limited in our linker chemistries to get that site-specific release. It is a challenge to increase the drug-antibody ratio. We've only got about, most of them, the maximum you can carry is about 8, and if you've got hydrophobic drug, it's even less than that. And tolerability and toxicity in that therapeutic index, even though they've got the efficacy, is still challenging, as is tumor tissue penetration and distribution. So we're working on our targeted dendrimers to try and address and really try and complement antibody-drug conjugates. So the system we're working on is a generation 5 polylysine generation 5 dendrimer, polylysine core, so that gives you 64 functional groups. Half of those functional groups are covered by this sarcosine polymer, and that provides a stealth layer, so when it's injected, we can get long circulation and it's not recognized by the body's immune system. And the other half, the other 32 of those 64 groups, we put a drug molecule on, and we link the drug molecule with a hydrolytic linker that is acid cleavable. We can then add a ligand onto the surface of the dendrimer, or a number of ligands on the surface of the dendrimer to target to a particular receptor. These dendrimers are about the same size of antibodies, so really sort of naturally occurring, similar to naturally occurring proteins in our bodies, so they're about 10 nanometers, and they're large enough to be eliminated, not be eliminated by the kidney, but still get tissue penetration and provide a degree of long circulation. And we've also designed those for ease of manufacture, which is really important when you've got complex medicines. So just run you through a particular case history here. So this is with a HER2 targeting ligand. So HER2 is a receptor overexpressed on many cancers, particularly breast, but gastric and a number of others as well. And here what we've done, we've carried a toxic, a topoisomerase SN38, and put this on our dendrimer. So in the non-targeted dendrimer, we get very, very little association with cells overexpressing that HER2 receptor. And when we've put the ligand, the Fab ligand on here, on the cells that shown in black that don't have the HER2 receptor, we get little association. When we've got the HER2, we're getting association with the cells. If you just look at the microscopy here, and then we did a colocalization assay to see what had colocalized with the lysosomes within the cells. And you can see quite clearly here, it took a little bit of a while, but after 24 hours, when you've got a ligand on, you've got nice colocalization with those lysosomes. And in just a cell assay here, these are quite challenging to do with hydrolytic linkers, but you can see with the addition of the ligands, we've got greater cell kill, greater cell death when you've got a ligand on than when you haven't got a ligand on. So we then took that system in vivo, and we looked at the did some UV vis just to see where it was going in a biodistribution study. And just to point out here, we've got all the organs here, and you can see that lighting up very nicely. You can see the ones with the low and the high ligands, so both the ones with the ligand on. But if you just look at particularly the tumours, you see those with the high ligands, we've got more radiance than we have with the low ligands. And when we actually quantify that radiance, you can see, when we've got the low and the high ligands over time, and particularly at 96 hours, and it takes a while to accumulate within tumours because of the long circulation, we're getting a lot more radiance. We also fluorescently labeled our dendrimers to see what was happening in terms of tissue penetration. And so that's a dendrimer with no ligand on. This is a dendrimer with 3 of the ligands on. So you're adding 150 kilodaltons in weight to the dendrimer, but you're still getting more into the tumor here. And then we did some image analysis, and we can just see here with the non-targeted dendrimer at both 4 and 96 hours, we didn't see very much associated with the tumor cells. We saw a lot more, particularly the 96 hours, associated with the stroma cells, but we need it to really get to the tumor cells, to kill the tumor cells. But with the HER2 labeled, we saw a lot more with both the tumor cells and the tumor to stroma ratio was a lot better. So generally a lot more homogeneous distribution within the tumor. And this really paid out in terms of efficacy. What I'm showing here is a comparison with a optimally designed antibody drug conjugate carrying just 8 drug molecules with the same dose of drug versus our dendrimer. And we can see here that without any ligand on, we get reasonable tumor growth inhibition compared to the control. So this is tumor volume over time. And yet we've got very, very similar efficacy to something that's doing very well in the clinic. So I think this is important for the platform, that we can actually mimic that, because there are only a few antibodies that will behave as well as this Herceptin. And we think we've got a lot more flexibility here. So I think what we think we've got here is a nano delivery system, a targeted dendrimer that can complement ADCs, and we can get more drug loading. We should be able to get to more targets, and we should be able to use the multivalency to get more selectivity and work to different tumor types. So that is my first example. I wanted to move on now to talk about lipid nanoparticles. So a very different technology, difference in terms of size, so 10 nanometers going up to 80 to 100 nanometers. And most people will be aware of these from the COVID vaccines, but they contain nucleic acid in the middle. They're made of 4 lipids. The important lipid, which is about 50% of the LNP, is the ionizable lipid. And then you've also got helper lipids, which tend to be a phospholipid, cholesterol, and then a PEG lipid. They've named, here you can see just those are the like numbers. Just show you the number of molecules of each within an LNP. And the important lipid is really the ionizable lipid, which complex with the nucleic acid and is probably the most important lipid in terms of endosome escape and efficient intercellular delivery. And that tends to be made of an amide head group, a linker, and a hydrophobic tail. It's important that we can have delivery systems such as that. Most of the drugs that we work with at the moment are small molecules and antibodies that act at the protein level and interfere with protein-protein interactions. But as I said before, it's limited. The drug space that we can prosecute that way is limited. If we can work on the way to the protein, either knocking down mRNA with the silencing RNA or producing the protein itself or editing the protein, we can prosecute and have drugs for a lot more diseases. So what we've tried to do internally and other people are trying to do is really to try and put a roadmap to get these LNPs to the clinic. And the important thing is to make sure that we can design the right LNP early on for the right tissue. And so we've put together a design, make, test cycle to design the lipids, synthesize the lipids, and then we build up understanding through a number of tests to try and get the optimal lipid in terms of both efficacy and safety. But it's also very important that they're stable and that we can manufacture them so that we can scale up. So we've put together a number of high throughput screens, both a formulation platform that we can try and use minimal quantities to actually make the lipid nanoparticles. This nanoprofiler assay, which is a really nice assay put together by a colleague of mine, and the paper is down there, where we can put the LNPs onto cells and we can look at cell uptake, we can look at endosomal release and protein expression, and they don't all correlate, but we can actually get to the bottom of what is the blocker in terms of protein expression and the efficiency of the LNP. We're also working on a number of high-throughput platforms to look at the protein corona, because that really affects the distribution of the LNP within the body, and a barcoding platform so we can more rapidly do some in vivo studies. So working with our chemists and working with some common core robust chemistries, we were allowed to run things through this design, make, test cycle. And you can see here that over time, we've actually managed to improve the amount of, this is EGFP protein, which is expressed in the liver. So this is for a liver lipid. And with each iteration, we get more and more protein and more efficient LNPs. This is just a little bit of a case history showing you that we can select lipids and formulations. So we made 250 LNP formulations. We characterize them for size, polydispersity, and to check that they work well in terms of encapsulating the RNA. And then we can look at the protein expression. And by using this high throughput system, we can really choose the right formulation and the right lipid that is most efficient at producing the protein, if it's producing protein, or if it's gene editing, with the gene editing card going for gene editing. And our record by doing this was a 320-fold improvement from where we started. So just in terms of thinking about LNPs, I've said that we looked at EGFP in the liver. LNPs nicely go to the liver. And that means that people are trying to develop them. Some of the first gene therapies are for liver diseases. And they do this partly because of the dynamics of the liver. It's a fenestrated tissue, and it's a very, excuse me, it's a very vascular tissue. But what happens when the LNP is injected into the body? The PEG lipid desorbs, and ApoE adsorbs onto the surface of the LNPs. And that ApoE is then, as it goes to the liver, links and interacts with the LDLR receptor, and which is overexpressed on hepatocytes. So that's what the reasons for the main reasons for the liver tropism. And just showing you a study here, which was done by the group in a paper put out by Moderna, is when they used ApoE knockout animals. So this is a wild type, the dosed LNPs, no ApoE, or no LDLR receptor, used knockout animals, no protein expression. So just really confirming the dependence on ApoE and LDLR for liver diseases. I just wanted to show you one example that I got from a colleague. So this is a disease, amyloidosis, which is really dependent on the TTR gene. There are a lot of drugs that have been given down here, but they don't really reduce the TTR levels that's needed in patients. There are siRNA out there, which gives you a knockdown of the protein, giving you about 70% reduction of the blood plasma levels. But what's really making the difference is the gene editing approaches. And this is some data from Intellia Therapeutics, who are the furthest ahead with the gene editing using CRISPR-Cas. And this will just show you, so this is a mouse TTR immunohistochemistry, and you can see, within one dose of 1 week, you've really knocked out that TTR. It's very, very clear. And so in 6 months after one LNP dose, a real knockout of that gene. And this is similar again. This got it from Laura, who's CSO of Intellia Therapeutics, just in 2 separate patient groups. Really, really clearly a dose dependency, but really, really clear, really reducing the blood levels and really showing that how one treatment is making a huge difference. And that's a lot better than perhaps the drugs we had by just really knocking down at the gene level. So just before I pull this together, just wanted to really share the delivery status of LNPs. and where we are now. So I think everybody's aware, and I've mentioned several times, that the vaccines, that's intramuscular delivery. They'll probably be used as a plug-and-play platform. We can move quite quickly with that, and they tend to have mRNA in there. I've mentioned that we can get to hepatic delivery because of the natural tropism. There are also, the furthest clinical trials are in phase 3, and there are also clinical trials for inhaled and eye diseases, so local delivery. It's a little bit harder to get extrahepatic, but there is a lot of work, and we're working in this space as well. And getting to the bone marrow and immune cells, another fenestrated tissue, getting to the spleen. So if we can do in vivo CAR Ts, if we can do that, and the muscle and the brain and the heart are really going to make a huge difference. There's a lot of work out in that space. I wanted to just mention something about intracellular delivery. So all these nucleotide drugs that are important for gene therapies and knocking out genes, they're all highly charged. They need a lot of help about getting in through that lipid bilayer into the cell. And it's estimated that only a couple of % are actually get into the cytosol. So your bioavailability of the drug is very low. You're throwing about 98% of the drug away because we haven't got efficient delivery. So efficient intracellular delivery is going to be really, really important. So we've done a lot of collaboration in this space with a number of groups to try and really understand or help understand more what is going on here. So I think we found out through collaboration both with the group at Hardie and the Swedish Drug Delivery Centre Formula X, that most of the escape is from the early endosomes, that it's the electrostatic interaction between the excess ionizing lipid in the LNP and the inner endosomal membrane as a pH drops that is important for that initial fusion. There's an LNP collapse that's hypothesized to occur soon after binding. We think there's a 1-to-1 mRNA lipid ratio that is present in worm-like mice cells that actually stays intact as the LNP collapses. And it's the fluidity of those lipids, and they're the ones that are more likely to form the hexagonal phases that are the ones that are liable to be more efficient. So there's a lot there, and there's a lot more work in this space. And I'm just trying to perhaps summarize in boxing some of the outputs, some of the papers and the collaborations we've had with a number of groups in the last few years. And we're really interested in trying to understand this more so we can design better systems. This is just from one of those papers, and this is just one of the ionizable lipids and cholesterol mix, and just showing you what's happening as the pH drops and that change into that hexagonal phase that occurs, and it's that hexagonal phase important for the endosome escape. And now being able to do some coarse grain and atomistic models to add to our understanding and the fundamental understanding, and hopefully by doing that we'll get more efficient delivery systems. So in summary, hopefully I've illustrated two very different nanomedicines for future medicines. Both targeting will continue to be important, and I've illustrated the lipid nanoparticles for nucleotide-based therapeutics. Hopefully, I've also illustrated that I think delivery science is going to be critical for the next generation of medicines. We need to make sure we get the fundamental understanding as well to design better systems, and it's going to be really, really important that we continue to collaborate across multidisciplinary boundaries. And before I finish, you want to acknowledge many colleagues in the Advanced Drug Delivery Group who have worked on the different modalities and platforms that I've described in a lot of this work. For the targeted dendrimer work, just call out Richard England, Sylvia, and the team at Macclesfield. And I showed you a little bit of the modelling from one of our postdocs, Lisbeth, and really a number of colleagues that have supported us with the in vivo work across the AZ sites and our external collaborators. And thank you for your attention.
Thank you very much, Marianne. Fantastic talk. We have time for a couple of questions.
Thank you very much, Prof. It was a wonderful talk. My question is, So by this method or therapeutic strategies, what you have proposed here and discussed, so can we regulate the microsatellite instability that can control the evolution of P53 kind of genes and can regulate the APC adenomatous polyposis coli?
Sorry, can you ask it?
Oh, yeah. So,
and I'm not sure I can answer it, but I'll try. Yeah.
So my question is, brief, it is like, can you control the genetic mutations, like particularly the microsatellite instability that causes further the adenoma carcinoma sequence kind of? Still, it's hypothesis and people are testing it. Or is it capable to regulate the APC regulations? I mean, kind of adenomatous polyposis coli that preserves the body to go for the higher state of carcinoma or kind of metastasis?
That's not an easy question, and I'm not a geneticist or whatever, I'm a delivery scientist. I think most of what's gone into the clinic for gene therapies has been a relatively simple gene that we know that if we affect or edit the gene, we know the cause and effect. I think there's a little bit more complexity in cancer because it's multiple genes. But I think if you've got a gene that is dependent, that you know is dependent on a particular cancer type, you know, there are certainly papers and some nice preclinical data showing that. P53 is a little bit complex. I'm not even going to try to answer that with a large audience, but I'm really not the person to ask that question. But I think we will get there, and there will be specific genes that we can modulate that will affect cancer patients as well.
Hi, Marianne. Very nice talk. With these lipid nanoparticles, how sensitive are they to the size and complexity of the RNA? Is it all about the lipids, or do you have to redesign your system for each RNA that you're going to try to deliver?
That's not an easy question, Paul, either. So you can encapsulate most things in an LNP, but we have found that if you put them on the high throughput screen for an mRNA, what is the best for an mRNA isn't the same LNP that's the best with the gene editing cargo in. So they are cargo specific. I don't think enough people have studied them on the fundamental level, you know, with endosome membranes, et cetera, understand what's going on, but one size definitely doesn't fit all here. So they'll work, but probably not to the most efficient level that you want them to. And I think you've always got to optimize, in my experience.
Okay, can I ask a much more general question, which is about working between industry and academia? And so if we have people here interested in working with AstraZeneca, could you say a few of the models or how the ways of working could be, or what succeeds?
Working at AstraZeneca or with?
With.
Okay.
Yeah.
I guess there are a number of different, you know, the number of groups, and we do try and collaborate. And, you know, I've tried to illustrate with a couple of groups, you know, fundamental problem, we think, you know, longer term research, let's try and work with academia. We do work on joint grants with people, trying to provide translational input. We have an open innovation program and co-solve programs. It's all on our website, and you can go and look, and that we kind of put challenges out there and people can apply, and then we support them in some ways. If you're looking for a postdoc, we have about 100 and 130 industrial postdocs, and then that, you know, that is meant to be pre-competitive work, doing an industrial postdocs. If you're not sure whether you want industry or academia, there's perhaps a choice to just have a taster of industry through a postdoc. Number of centres of doctoral training for PhD students. And if you think you've got something interesting, you know, we do contact us, collaborate. We do have academic alliances, groups, and people that go out and look for new technologies and things that may make a difference. I don't know if I'm trying to summarise off the top of my head. Yeah. I need to finish.
It's also a more general question regarding regulations. When you create a drug delivery system with, what's the criterion for patents and things like that? Because if you have a patent small molecule, for example, being used within a career, how does it work?
Okay, so if we as AstraZeneca want to use somebody else's molecule in our delivery system, we would have to take a license. So we would either have to design our own molecule, all take a license, and we'd always try and patent something because we obviously need to protect our investment. I'm not sure if that's ours, because you asked a regulatory question as well.
With the small molecules in the carriers, can it change, for example, the polymorphic form of this during the preparation of the...
So I think it depends what you do with it in the carrier. So we tend to conjugate ours, so we actually change a different chemical entity because we actually put a linker there. Okay. But that also strengthens the pattern. So you've got a different component there. If we're doing amorphous solid dispersions, which I showed up but didn't talk about, you're obviously changing your polymorph, or you change it to an amorphous form. It doesn't really apply for the LMPs because we're working in nucleotides. So we do change things, and you will have to have a separate, from molecularly drug substance package and a drug product package, and you'll have to repeat your tox a lot of things, because a lot of what we're doing is changing the distribution in the body and the in vivo performance, so you therefore need to repeat toxicology. Does that answer the question? Thanks.
Thank you very much. Can we thank Marianne again? Our next speaker is Professor Ruth Wilcox from the Institute of Medical and Biological Engineering. And she probably doesn't really need an introduction, because if you have to do anything with health tech in this university, you will have come across her. Ruth has been very active in translation of health technologies. She has been leading the IKC in MedTech some years ago, is now leading our PBI, our place-based IAA account, again, with view of translating technology. She's also the director of Health Tech Leads. So anything to do with health tech, it is Ruth. And thank you very much for coming and talking about devices and translational activities.
Can you hear me now? Thank you, Christoph, for the introduction. I guess I have a bit of a disclosure to make at the start, and that is that I'm a mechanical engineer by background, and I really work in the millimetre scale most comfortably, maybe down to the micrometre, but I really don't work at the nanometre scale at all, and that kind of brings me out in a bit of a cold sweat to see that I was talking in this session. So fortunately, Marianne has covered nano really well, I think. So I'm going to focus more on the bio and the technology part of the title of the session, I suppose, here, and particularly look at larger scales, so medical devices in particular. Talk a bit about what we do in the Institute of Medical and Biological Engineering at that kind of larger length scale, and a little bit about sort of maybe future opportunities, particularly in the biomaterials space. So my slide seems to have decided to progress anyway, so it's clearly time to move on to this. So I'm the director, as Christoph says, of the Institute of Medical and Biological Engineering. We're a cross-disciplinary research institute here at Leeds with academics in mechanical engineering, such as myself, and colleagues in biomedical sciences as well. And really our research is around applying engineering principles to evaluate and optimize medical devices. We focus particularly on musculoskeletal devices, so bones, joints, and devices to treat injuries or diseases of those tissues, and also cardiovascular devices. So really where the mechanics and the biomechanics is an important part of the function of the device. And we look at two different areas, really. We look at developing new therapies and also improving existing therapies. On the developing new therapies side, we work closely with academic colleagues, including here in Bragg. On the improving existing treatments side, we work more closely with industry and with our clinical colleagues as well. And what really underpins both of those two areas are the tools and techniques that we use in engineering, which are around preclinical simulation or prediction, if you like, of how these devices will behave for potentially long periods of time in the body, and how we can evaluate those and optimize their design and their use in clinic. And we use a range of different techniques, including in vitro mechanical testing using a variety of bespoke machines to test out these devices in our laboratories, and very much more now computational modeling as well, particularly using finite element analysis techniques to evaluate, for example, a wider proportion of the population and the variances that we see across a population. I've just popped onto this slide some of our main funding or main grants that we've received over the last few years. And you'll see that EPSRC is our main funder, but the important thing really is that the investigators that are associated with those awards are different people. And really, I think our strength as an institute is being able to bring together different expertises around engineering and around biological sciences as well, together to tackle different clinical challenges. And we also work very closely with our clinical colleagues. We're very fortunate here in Leeds to host one of the NIHR biomedical research centres, which has particular foci around cardiovascular musculoskeletal diseases. So I put up this slide every year when we have our new PhD students coming in October time. I probably bore the PhD researchers that have been here for longer, but I think it's really important that we kind of consider what the clinical drivers are for our research. And I focused this slide particularly on our musculoskeletal devices, which is what I'm going to talk about particularly here. So over 10 million people in the UK have osteoarthritis. 6 million people have what would be described as chronic back pain. And those two diseases on their own cost about 30 million working days per year in terms of the UK workforce. And if you add up the healthcare costs, the associated social care costs and the welfare payouts, then in actually most Western European countries, that accounts for about 1% to 2% of gross domestic product. So this is a really big economic issue as well. And it has knock-on effects. So half of musculoskeletal patients report that there's a barrier to them being physically active. That has implications for their physical health, for their cardiovascular system, and so on. It also has implications for their mental health as well, with patients being much more likely to report depression. So it's really important from a society point of view, from an economy point of view, that we try and tackle and treat these kinds of musculoskeletal conditions and prevent this cascade of ill health and support patients to get back to work and back to physical activity. So I'm going to focus on two examples, like Marianne. They're very different cases here in this talk. But first, I just wanted to talk a little bit more generally about the kind of design considerations that we'd have for any musculoskeletal device, really. This is not in any way an exhaustive list, but I've kind of bunched this into some different areas. And I suppose here, when talking to the Bragg audience, it might be the materials choice that's particularly at the forefront of our minds. And there's certainly a lot of different material requirements for any kind of physical implantable device that we're going to put into the body. But there's also then what happens when we put these materials together into a device. There's the device design and a lot of requirements around that, how it will be then fixed into the body and how the load will transfer, how it will be manufactured. So there's a lot of design considerations as well. And then there's the implementation side too. So the surgical procedure, how can this actually be implanted surgically? What additional tools are going to be necessary to make that work? And how will the patient perhaps be rehabilitated afterwards? So our work is really about trying to bring all of this together and consider all of these aspects of the device design and then predict how the device in a particular patient will behave over longer periods of time. So as I said, I'm going to pull out two examples, talk a little bit about what we've done, and then perhaps draw some conclusions about what the future is, particularly the potential for new biomaterials in this space. So I'm going to start with total hip replacement. This is really a very established technology developed back in the 1960s. John Charlie, the picture there, was one of the first surgeons in the UK who really pioneered the treatments. A lot of the early devices were actually manufactured here in Leeds, and there's been active research at the university really since the 1970s around hip replacements. The very earliest designs had a real issues with wear. There's an example there on the right-hand side of a Teflon hip replacement that wore out very quickly. Even once the materials have been changed to higher wear materials, the wear particles that are produced over the course of their lifetime can have a biological effect and induce osteolysis that causes the device to eventually loosen and need replacing. So as I said, there's been research at Leeds really since the 1970s around developing methods to understand the bearings, particularly in hip replacement, and the materials from which they're made. So a lot of work in the laboratories to develop tools to simulate how these devices behave in the body over hundreds and thousands and millions of loading cycles, and then work with our biological colleagues to evaluate the effects of different sizes and shapes of wear particles and how the body deals with those. And these advances have really helped to bring on new generations of much higher wearing materials that, for joint replacements, particularly higher wearing polyethylenes, but also hard bearings made out of ceramics that have drastically reduced wear-related failures of these devices. Some examples down at the bottom there, revision rates really very low at 10 years. Even by 25 years in the body, then we're still talking about a 60% survivorship. So this is clearly a success story where the testing that we're able to do has helped to inform the material design, and together those things have helped to improve the longevity of these types of devices. It's not quite a done deal, though. I think we're probably at an end to where we can get to with the materials of the bearings themselves in terms of balancing the different requirements there. But we do have new demands. Patients are getting younger, they're more active. There's also a cohort of patients living with obesity. Those things are putting increasing loading demands onto our joints. As I said, the bearings themselves are probably at a point where they can't evolve that much more, but there's a lot of opportunities around the surgical technique itself, the choice of device for particular individuals that are tuned to their needs. And indeed, there are definite advances in technology that can help us with this, whether that's around detecting how patients move before they go in to have their treatment, or monitoring the device once it's in vivo through smart devices or wearable sensors. The second area that is increasingly becoming a problem is around infection in these devices after they've been implanted. And because they're deep in the body, those infections can be difficult to detect and then difficult to treat. And obviously, AMR is causing greater concerns around the prophylactic use of drugs to stop that from happening. So I think there's a lot of opportunities here as well for the biomaterials community, whether that's around novel coatings for the devices that can help prevent infection, but also around biosensors that can detect the infections very early and potentially cause a rapid targeted treatment of those infections too. And indeed, we have several projects in the pipeline at the moment with colleagues in Bragg to start to look at different potential solutions to these problems. So that was the first area. The second area then I wanted to talk to was to move to the spine and particularly talk about surgical interventions for disc degeneration. So the discs are the soft tissues in between the vertebrae in our back that allow us to articulate. They have, in the healthy state, they have a gel-like structure in the middle surrounded by a fibrous outer ring. The gel draws in water, it has a lot of proteoglycans within it, and that helps us to maintain the height and enable those to articulate. But as they degenerate, that gel structure starts to break down, the discs lose height, they don't draw in water, and that's when chronic pain can start. So one potential treatment is that if we can get in early enough and inject a biomaterial into the nucleus of the disc, we can effectively plump the disc up stop that reduction in height, and potentially stop that degenerative cascade that eventually leads to pain and the destruction of the disc. So we started working on this problem about 15 years ago. Actually started with some workshops where we brought together both clinicians and biomaterial scientists from around the UK to try and work out exactly what the design requirements would be for such a device to be successful. And then we teamed up with a group in chemistry here at Leeds who had been developing a set of self-assembling peptides, or a family of self-assembling peptides, that have a lot of the properties that were potentially suitable for this type of device. We undertook a pilot study as a PhD study, actually, where we looked to see whether we could incorporate glycosaminoglycans into the peptides, and found not only that we could do that, but that actually acted as a trigger to help the gelation of the peptide and to support its stability as well. And the incorporation of those GAGs into the peptide also then helped it to mimic the natural tissue and draw in water. So that was 10 years ago, a little bit more now. And that started really a long multidisciplinary journey. And I won't go into all of the steps of this in any detail, but we worked with colleagues in chemistry on the materials characterization, found that we could tune the properties quite well within the range that we wanted. We undertook a lot of in vitro testing over in mechanical engineering and also in biology to look at the biocompatibility. We developed some imaging techniques that were necessary for this to become a clinical product. We developed a delivery system, and importantly, we could deliver this peptide hydrogel as a liquid down very, very fine bore needles so we don't damage the surrounding tissue, and then it forms a gel then in situ once the components self-assemble. We had to investigate the sterilization of that, and then in the last 2 or 3 years we've moved on to the first large animal studies. Again, that was problematic because a model doesn't actually exist yet for this type of treatment, so we had to do quite a lot of preliminary work to identify an animal in which we could do this test. And then we undertook the testing over the last couple of years with colleagues in Nottingham and in Cambridge. The upshot of this story is we're not there yet, but we've so far shown efficacy and safety in all of the tests that we've done. So we're now really at a position to start moving towards the first in vivo human trials, and working with our commercialization office and colleagues across the university to do that and to bring in some industrial partners to help us on the journey towards eventual, we hope, clinical products. So really, I wanted to use that example to illustrate just how many different disciplines are involved, have been involved in this study, right from the material scientists and the chemists, and Paul Beals in particular has been a great input on the basic science side, right through to our clinical colleagues who are helping us to ensure that the technique is translatable into clinic at the end of the day. So finally, I just wanted to come back to those design considerations. And really, I suppose this is a message I think that Marianne brought out at the end of her talk as well, that the collaboration is absolutely key here. So we're in a great position here in Leeds because we have this fantastic Bragg facilities and expertise here that can help with that basic materials development side of things. We also have the other end, the clinical end, through the NIHR and other, particularly NIHR funding through the Leeds Biomedical Research Centre that can enable us to keep that clinical practice in mind as well. So, and then I suppose my institute and others around us are sort of that glue a little bit in the middle to help us to move along that translational pathway. So to draw to conclusion then, to address today's pressing clinical challenges, particularly in the musculoskeletal area, but I think we've heard this is true across all areas of clinical practice actually, we need to optimize the current procedures that we have, and we need to develop completely new ones, and there's opportunities with new biomaterials certainly to do that. So we need novel biomaterials for the device themselves, but also for coatings, for the biocenters, for all of the supports that's necessary for those devices as well. And the only way that we can really do that, I believe, is to harness expertise across the biomaterials sector, but also the device design and evaluation and the clinical application fields as well. So finally, I'd just like to give a little bit of a shout out, as Christoph said at the start, to Health Tech Leeds. This is a new initiative that we have here at Leeds to try and bring together the health technologies research across the university. We have a launch event. I've just realised I might not have written down the date of it. It's the 26th of March. You will be receiving invites shortly, and we really hope to come along. We hope to really help to build the community across the university that's working in this area. And thank you very much for listening.
Thank you very much, Ruth. Are there questions? Well, maybe until you thought of your questions, I will ask a question. Can you give us sort of an indication of the timescales that are involved from, you gave us that example of the lower back pain and the injectable peptide. So from coming up with or realizing there's a problem until the solution that you developed is in fact in the clinic and available to patients?
Yeah, so a figure that's often quoted is 10 years, but I would actually say that's pretty optimistic. And really that 10 years is starting when the device is starting to be properly developed and put together. And really, I would say in many cases it's more like 20 years from the real biomaterials initiatives that might come on, the changes in biomaterial or a completely new device concept getting through to clinic. And that is clearly a challenge for all of us working in this field, that those timescales are so long, and there's potential things that we can do to try and speed that up. But there is an awful lot that goes into that device, and we need to satisfy a lot of regulatory procedures and make sure that each stage of that design is as robust as possible before we move on to the next one, which inevitably involves a lot more money. So I don't think there's any really quick answers to that, and that's just to some extent what we have to accept working in this field.
You did say that it could potentially be sped up. Could you just elaborate?
I'd say the bit that could be sped up is where it gets to where we've moved from to the prototyping kind of phase, where we've perhaps shown some initial proof of concept. And there, I mean, it's called a valley of death for a reason. There's not a great deal of funding in that space. It's past the point where kind of EPSRC think if this is an exciting new thing. It's not at a point yet where industry would potentially take it up because it's still too risky. Very much there's a stage there of hopping from small project to small project to small project to take something forward. And that is the stage that a lot of these technologies fizzle out, not because the technology is bad, but just because the effort in getting the next piece of money compared to getting the next piece of money to do some nice basic research gets a lot more challenging.
So that's the stage you're talking about. There's obviously the funding bit to do that. There's also the regulation, I guess, at that point. Is it the regulation as well that could be, I mean, can you say something about the regulation and whether that could be sped up as well as making funding available to do things?
Yeah, I wouldn't say the regulation is necessarily the slow part, particularly. And we had to be careful. These devices obviously need to be regulated and safety has to be paramount. But what can happen is that the regulation hasn't caught up with the technology, right? So the regulations are all based, the standards that we have to comply to don't really apply to the types of technology that we're working on. Generally in the UK, I would say the regulators are quite good at understanding that and actually working with groups to try and figure out a way through that. So that's not normally the barrier compared to the funding, I would say, at this stage.
Good. Thank you again, Ruth. Thank you very much for a very interesting talk. And we have come to our final talk of this Bragg Exchange. And it's a pleasure to introduce Joe Fox. And Joe has done his PhD in the School of Physics. During his PhD, he worked predominantly on drug delivery systems, sort of a bit similar to what we heard from Marianne. But he has moved on and is now doing his postdoc and developing diagnostics based on using gold nanoparticles. Thank you, Joe.
Can everyone hear me okay? Nope. Can everyone hear me okay? Thank you. Hi, everyone. Yeah, I'm Joe. I'm a postdoc working in physics, and we're working on a new project which is about the synthesis of novel gold nanomaterials for the detection of urinary tract infections. So I'm going to talk a little bit about the background, the materials, the problem we're trying to solve, and where we're at and what we've done kind of in the preliminary work and the proof of concept work. So the problem that we're out there trying to solve is urinary tract infections, and these arise when bacteria, usually found in the gut, invades other parts of the body. So that could be the urethra, the bladder, the kidneys, and then eventually you can get sepsis where this bacteria invades the blood. The most common UTI-causing bacteria are E. coli and Klebsiella, but there's a range of others. And NHS England recorded nearly 2 million UTI-related hospital visits within a 5-year period, all with different severities, so it can be life-threatening. The current solutions for detecting these in a patient is to actually take a sample of the urine, send it away to the lab, culture it, and optically assess it. So that can take a few days. And a really large cohort study showed that 86% of patients receive antibiotics while that assessment is being done. So they're given antibiotics which are a bit empirical and not really targeted to the bacteria that they have. So there's also dipstick tests, but these, again, they will identify that there is an infection, but not which specific one. So the antibiotics that are given are, again, just general. They're not really targeted. And these two feed into the inappropriate prescribing of antibiotics, which drives antimicrobial resistance. So the proposed solution that we have in our group is we think that we need a cheap disposable test to quickly identify and also quantify the concentration of bacteria in a sample. And we work on lateral flow assays. So the idea would be a multiplex test with multiple test lines where each line corresponds to a different bacteria that could be found in the urine. We think this would cut the diagnosis time. So from having to send it to a lab, which takes 2 to 3 days, potentially these tests run in 15 minutes. It would help with home testing, and the NHS has a big drive on remote consultation, so that's phone tests and video conference GP appointments, and it will just enhance treatment. And the idea would be that the GP would have a table a bit like this, and if you've got test line 1, you have bacterial infection 1, and you go to antibiotic set 1, and then would have a matrix of all the different combinations, which is informed by what treatments would be for those infections. So a bit of a whistle-stop tour of how the test works in principle. We have our sample, which would be urine, and this green blob is the bacteria. We have our gold nanoparticles, which are spheres in this example. Those gold nanoparticles are bound to an antibody to detect the bacteria. We also have another antibody for the bacteria on the test line, so we'll make this sandwich as everything flows past. And we have a control line which binds any antibody just to confirm that the liquid is run fully. So when we run it, the bacteria lands on the sample pad, moves into the conjugate pad, and is picked up by our gold nanoparticles bound to a bacterial antibody. This then moves up the test and sticks at the test and control lines and gives those distinct red bands you'll have seen in COVID tests. And it's the gold nanoparticle that gives the red coloration. So our idea would be to use an array of different antibodies for different bacteria to create these multiple line tests. One of the challenges might be that having these in a line creates a bit of interference between the two. So one of the other lower risk options is to make an array of tests where you'd have each one separate, but you only add the sample once. Something that's a bit novel to our work is we make a whole range of different shape and size gold nanoparticles, and they all have different colors in solution. So this does give us the option to give a test with the different lines of different colors, which is just a bit of extra clarification for a home use situation. And we're going to use a combination of novel materials developed in Leeds. So the nanoparticles that are often used in lateral flow tests, like you see in the COVID tests, are the spherical gold, the red in solution, and they give a red test line. There's a lot of literature that suggests that hierarchical or rough structures would be better for lateral flow, mainly around the idea that the rough surface has a lot more area for antibodies to absorb onto. And there's a few papers coming out that say that these particles give improved lateral flow performance. So in Leeds, we've started to get into hierarchical materials. The journey starts with, just before I came onto the project, I did a big piece of work on creating 2D gold. So this is atomic layer, sub-nanometer thick 2D gold, done by a really neat synthesis using methyl orange as a confining agent. And it's the first freestanding 2D gold and has a really high catalytic activity. So where my work has come into the project at the end of my PhD was looking at optimizing that synthesis, trying to understand how it works. We did a lot of spectral analysis during the synthesis, a lot of optimization of parameters of the synthesis, and we found that as well as being able to improve the yield of the gold sheet, we can easily tune that synthesis to make other really interesting structures. So if we just, for example, increase the spin speed when we've made these, we can create these strands, which we call gold nanotapes, which I think there was Nizzy's poster was working with this material. And likewise, if during the synthesis, if we use a higher confining agent concentration, we can generate these, we call them the gold nanopine cones. So they're around 90 nanometers, and they're hierarchical, which is of interest to us for lateral flow. All these nanoparticles, so the nanotapes, pine cones, and sheets, we think have a 2D property, just kind of informed by their UV vis. So they have high absorbance in the near infrared, which would imply they've all got kind of an element of 2D. And we know from AFM that the sheets and the 2D and the tapes have a 2D element. So interestingly, the tapes, as pointed out in one of Nizzy's posters, are very catalytically active, much more so than spherical gold. And what's interesting about the pine cones is that they can be synthesized instantly. It's scalable and they're hierarchical. So we've employed these particles, so the nanoparticles, which are spherical, the nanopine cones, and the nanotapes, into a proof of concept assay detecting a biomarker for cancer called CEA. And we've shown that the pine cones are twice as sensitive as spherical gold when used at a much less a lower number of nanoparticles in total. Some additional benefits of the pine cone, along with that improved lateral flow performance, is that when people in the literature tend to make hierarchical structures, it's a seeded growth done at high temperature and has many steps. So they form spherical gold first, do the cleaning, and then they do an extra step where they're adding more gold and a reducing agent, and it's all usually done under boiling. Our synthesis is seedless, done at room temperature, takes about 5 minutes. There's no harsh solvents, and we've shown that we can scale it and do it in quite big flasks. And we've also had a master student prove the concept that you could have it synthesizing continuously because it's so quick. You can have all the tubing with the different reagents coming in, and the particles are flowing off a chip. So where this is going to hopefully lead into our next piece of work, we've presented this work to a company in Derby who are one of the largest lateral flow assay producers in the UK, and they've provided us with all the instruments to make our own tests in-house. So the previous tests I showed, we were buying them and then functionalizing them with antibodies and gold. We now have all the facilities to actually make from scratch these tests. So we have an instrument at the top left, which is literally like a sprayer that sprays our gold conjugate. So this would be our pine cones labeled with an E. coli antibody. We spray that into the conjugate pad. We then have a second instrument which has these fine needle points which stripes across the nitrocellulose and sprays the test and control lines. We do this on quite a large card, and then we have a guillotine which cuts it up, and we can set them up to make an individual test. We then culture the bacteria, run the tests, and we have some MATLAB code that automatically tries to quantify the signal so we can get a concentration gradient. And this is kind of just new work now, so we're just coming on to doing the bacterial detection. We've got it working in Klebsiella, and we're currently working on improving the signal-to-noise ratio in Klebsiella and E. coli. So just to summarize, methyl orange-based synthesis can quite easily generate a range of gold nanoparticle morphologies. The gold nanopine cone could detect, is a twofold improvement for cancer biomarker detection over spherical gold, conventional gold. The pine cone production is simple, is seedless, and is rapid at ambient conditions. And we've just started the in-house production of these pine cone lateral flow assays for bacteria. And yeah, the future work is to improve the signal to noise and then start to produce these multiplex tests where we're detecting multiple bacteria on the same stick. And yeah, just like to thank, we're quite a big group over in molecular and nanoscale physics, and we've got the commercial partners down at show screen. Thank you, thanks very much.
Thank you very much, Joe. Any questions for Joe? Well, again, that gives me the chance to ask a question. When you test for these bacteria, and one of the things why you said that you want to test because of AMR, yeah. Could you at the same time also test for antibiotic susceptibility of the different bacteria that you find are responsible for the infection?
Potentially, I'm not sure how. You could run the test on a sample before and after it's been treated and see how much are still living after a treatment, potentially, because it's quantitative.
Okay.
So it would give the concentration of bacteria before and after a
so
treatment.
You could see the decrease in bacteria.
You could see a decrease in concentration. I'm not sure if you could discern whether that bacteria is resistant.
Okay.
But you could maybe use it to see how effective a treatment has been before and after.
Good, thank you. I guess we are a few minutes late, so people have to move on. So can I just ask the audience to thank all the speakers of the session again? Thank you very much.
Okay. And if you could, those that can, could just bear with us for 10 more minutes just to finish a few things like prizes, which I know that you're all going to be interested in. So I've got to now do a little bit of an intermission while I think a few people just disappear out the door to just consider the prizes, and it won't take very long. So could the EAB and Oliver just go down the side to talk about prizes while I talk to you while that's happening? So you've got about 2 minutes to come back in. No promise. That's all I can make up things for is 2 minutes. Okay. So I will say a few more things when our EAB come back in again, but I just wanted to just say before everyone disappeared, a few announcements about things that are upcoming. So firstly, I assume that most of you in the audience are already Bragg members, because that's how you probably knew about the event. If not, please join. And if you know colleagues who aren't, could you actually ask them to join the Bragg membership? Because we sometimes get complaints, well, quite often, I didn't know about. Why is the event here? And the answer is, if you don't sign up and we don't communicate to you, it's difficult if you know about it. So if you know people who aren't Bragg members, please do encourage them to join. And similarly, I would invite you all to look at the Royce Institute website. Lots of materials research going on there, lots of opportunities, lots of events. Look at that, because again, I don't know what Royce does. Well, there is an opportunity to actually get involved in some of that. So please do, and there are lots of events and funding opportunities, internship opportunities, all kinds of things that Royce offers. So please do that. Of course, I think you'll agree the exchange has been a success. I hope you do. I think we'll be booking very shortly for the Bragg Exchange 2026. That seems a long way away, but we'll probably have to book that in the next week or so in the same sort of period of time. And of course, if you have particular feedback about it, we would very much welcome that, particularly as we'll need to make a booking for here and the refectory, which is where I think we'll be next year. But of course, although the exchange is in a year's time, that's not as if things aren't going to happen in the meantime. So there's a few sort of upcoming things that's probably worth you knowing about. If you're a PhD student or have got PhD students in your group, we will be having our PhD colloquium in June. I don't think the date has yet been finalised, but in June we'll have the PhD colloquium. Really good chance for PhD students to practice talks, particularly before conferences in the summer. So please do encourage your PhD students, or if you are a PhD student, do come to that event in June. We will continue with our regular Lunch at Bragg events. We have two lined up. One is about the diamond light source in March, and I think we have a visit from the Royal Armouries in February. And the Royal Armouries are very, very, very interested, as far as I can gather, with working with the Bragg, I think, to try and understand some of their artifacts. So if you want to be something where you know about how they do aging and what's going on and where it was and what the steel was and what the metals are, come to that event and find out what the Royal Armouries would like us to do with them. So I think that will be an exciting opportunity going forwards. We had last year, for the first time, I think it was first time, a facilities open house event, which was open to people. We will again be doing that in 2025. And again, please do, if you came to it last year, please do encourage people to come to it this year, because it was a great chance to wander around the facilities in the Bragg Centre, see what we had, and perhaps think of the techniques that you might be able to use through research and you didn't know was just lurking round the corner in the Bragg building. So please do keep getting involved over the next year, prepare for 2026, and please do make sure you're on the list and do read that email when it comes, because we try and put some interesting information in the email when it comes to the Bragg Centre, so don't just put it straight in the bin. So that's my events, while hopefully the EAB is doing something useful outside, and I might, you're back in, are you? Where's Oliver? Oliver is doing some sorting out around the back. Okay, so that was my sort of events coming up, please do get involved in the Bragg Centre. I think since we've got a captive audience here, they're not rushing out yet, I think we should do also some thank yous. I think it's been a great event, and I think really a big thank you to all our speakers, all the people that have put the posters together, and I thought both the talks and the posters were universally absolutely fantastic, and it was really good to see all those posters. Thank you to our EAB who are dotted around the audience. Thank you for coming to join us, for asking questions, for doing some judging, and for telling us what they like about what we're doing and what they don't tomorrow, which is our joy tomorrow morning. EPSRC, good to have you with us. Our sponsors, and of course all of you who came to this event, because a lot of people have come who weren't either talking or giving a poster, but it's all of us working together that really is a great opportunity for the Bragg Centre. Right, I think we should be getting on to the prizes part. So Sheetal, is Sheetal? Popping out of the corner. Right, okay. So Oliver, Sheetal. Okay, just on time. I've almost timed that perfectly. Right, so I think the most exciting bit you want is now to know who's won the prizes for the talks and for the poster, or the talk and the poster. So, sorry? Poster prizes first. Right, I'm now being told what to do, which is usually the way, both in work and at home. Okay, so the runner-up poster. So poster prizes. Okay, I think you're doing the posters. Sheetal, we've got a little bit of a conferring down the bottom, and I want to hand over. Right. Sorry. Are you both coming up to do some prizes? We need some photography sorted.
Yeah, that sounds good.
Okay.
Hi everyone, I am Kay Burrows. I'm here from the Royal Society of Chemistry. I am with the RSC now, but I did my PhD here in the School of Chemistry, so it's really nice to be back on campus. I just wanted to thank everybody who's attended, everybody who's presented a talk or a poster, and the organisers as well, because it's been a fantastic event and I've had a great time. You probably know about the RSC as a not-for-profit society publisher for journals and books, but they do also do lots of advocacy work, lots of policy, education and outreach. I am here on behalf of 4 of our materials journals, which are on the slides. So the Soft Matter, Materials Horizons, Molecular Systems Design and Engineering, and Materials Advances, who have sponsored the poster prizes today. So without any more chatter from me, we are going to announce the prizes. Is that okay? We're good? Sorry. Okay, on this sheet. So, we've got 2 runner-up prizes of a £50 Amazon gift card. So the first runner-up poster prize goes to Oliver Eyre from the School of Chemistry with a poster revealing the mechanism of biomorph formation. Well done. Sorry. So the next runner-up poster prize goes to Ahmad Boromand from the School of Physics and Astronomy for scaling behavior of the mechanics and mesoscale structure of folded protein hydrogels. bit of juggling happening here. Okay, I'm ready. So the best poster prize goes to Dimitra, Katranci from the School of Chemical and Process Engineering for the poster Unveiling the Structure of Protein-Based Hydrogels by Overcoming Cryo-SEM Sample Preparation Challenges. Thank you very much, everyone.
Oliver now.
Well, good afternoon, everyone. For those of you who don't know me, my name is Oliver Graydon, and I'm the chief editor of the journal Nature Photonics. And I'd also like to just thank very much both Andrew and Edmund for inviting me to be part of this Bragg event. It's the first time I've been to the Bragg Exchange, but I've been really impressed, I think, by the breadth and the diversity and the energy that all of the speakers have brought to the event. And just, I think, I'd like to say to everyone here, please keep on doing it. I do think it is so important that universities continue to make a big effort to raise awareness, both internally and externally, about the breadth of what they're doing, because there's a real risk that people can become very one-dimensional and very narrow, I think, in their research interests, and I strongly believe that doesn't help foster good science. Now, without further ado, I'd like to go on and present the award prize for the early career best talk. We actually had 6 early career talks from 4 schools, from electronic engineering, medicine, physics and chemistry. And the prize winner, who will be receiving a 1-year complimentary subscription to Nature Photonics and a £100 Amazon gift card, is Joe Fox from Physics and Astronomy. Many congratulations, Joe. So come here and
Thank you.
Here you are.
Thank you so much.
All right. I'll just get that out of the way. So, Joe, my business card is in there. Just send me your complete contact details and I'll take care of the subscription for you. That's great.
Just before you I'm going to just invite Sheetal, who, on behalf of the External Advisory Board, just to say a couple of words about the event. A couple of words. Well, 2 minutes. Let's go for 2 minutes, and then I've 2 minutes, and then I've got one thing just to say at the end of it. So, Sheetal.
Thank you, Edmund. Can everybody hear me? Yep. I'm just going to put this down because I don't think it's working. Don't worry. I can shout.
You can shout. Used to it in your previous role. We need it.
Okay.
Yeah.
Should I try that one? Right. After that, so people who don't know me, I'm Sheetal Handa. I've been with the External Advisory Board for Bragg for 6 years, since the inception, I think. Yeah. So, and in that time, I'm already retired from my day job. So it's really nice to come and see this. And I've been seeing this Bragg Exchange since its inception. And I must say, this year has been fantastic. Not just the number of participants, but also I've seen over the years how the quality of the talks and the posters has gone up and up and up. So no pressure on next year's participants, but it's been brilliant. You know, who would know that the School of Physics and Astronomy would be working in UTIs? I mean, good heavens, that's amazing. So well done, Joseph. On behalf of the EAB, I just wanted to thank everybody, Edmund, the team, who really put this together. It's been fantastic. I think the venue is really good. The organization has been flawless as ever, and the quality of the science that we've heard over the last 2 days has been brilliant. So a big thank you to everybody. The EAB has a very easy job. We turn up, we moan, we might give a bit of direction, and we just enjoyed 2 days worth of science. So thank you very much.
Thank you very much, Sheetal. Of course, this event has been great. We've already enjoyed it. There's one little bit of sadness that was hinted at the start of the day by Nick, and that Andy has decided to go and do something else. Now, I met Andy I think it was about 5 years ago. Did you start? You see, I can't even remember the dates, but about 5 years ago, I can remember Andy sort of talking to me about the role and saying, wasn't quite sure it was the thing for him. I think it's fair to say, Andy, if I remember rightly, wow, have you made this a role for you, Andy? It's been fantastic. I mean, it's difficult to list all the things, but obviously the Bragg Exchange has evolved over the years, and I think we all agreed that it's worked fantastically. We've had lunch at Bragg's. We've had your own particular emphasis on DNA origami, which has been nationally recognised with awards. We've got all the stuff around the facilities, and I think our facilities and our facility staff really appreciate all you've done to try and make them feel part of the community. I could just go on. So thank you very much indeed. You're obviously moving to a different role, which is great sadness for us as Bragg, but we're really pleased you're still actually going to be in the University of Leeds. And you have promised you're going to come back and visit, and we do know where to come and find you. So you're not going to escape Bragg totally, and we will be getting you to put the Bragg Exchange in your diary for next year as soon as the dates are fixed. So please, we will do that. Just generally, we will have a new advert going out for I don't think I can really say replacement for Andy's role. That doesn't seem the right way of putting it, because I don't think we can replace you, Andy. But we will have, very shortly, recruiting for a new position to fill what Andy has left behind, which is a very big hole in the Bragg team. So we thank you very much for that. And if I'm right, hidden behind some kind of wall over that side, outfit might magically appear. Helen, bearing gifts. So Andy, thank you very much indeed for all you've done.
I'm juggling a bit now. Thank you so much. And it's been an absolute privilege and a pleasure to help support Bragg and build a community with you and all of the activities that we've done. I think the praise is really lovely. Thank you. But really, we've done it together. It's you, the community, that makes Bragg, not the things that I've done. I've just put them in place to enable you to get together and enjoy things. So this is wonderful. And I really do look forward to coming back to see the Bragg Exchange next year as a participant and sit at the back, enjoy the coffee, and not really stress about anything. Hope to see you all again soon.
So, thank you very much, everyone. Have a good rest of your afternoon. Some of you are going over to hear the LEMAS relaunch, and look out for that email which gives you the date for next year, and put it in your diary by the end of the month. Thank you very much, everyone.